Hello there, and welcome to Science for Sleep, the little corner where curiosity curls up in a blanket and science takes the scenic route toward rest. Tonight's quiet journey takes us far, far beyond our daily lives, past the warmth of the sun, past the swirl of galaxies, all the way to a question that sits at the edge of imagination. How does the universe end? Not tomorrow or next week, not even in billions of years, but in a future so distant it almost slips beyond what the human mind can comfortably hold. Among the many possibilities scientists have considered, there is one that feels both chilling and strangely peaceful. It's called heat death. Now, the phrase itself doesn't sound particularly inviting. Heat death. It has the ring of something final, as if the cosmos has run a marathon and finally collapsed in exhaustion. But before you drift too far into that image, it might help to know that this idea isn't about sudden explosions or fiery apocalypses. Instead, it's about a long, slow fading. The universe, step by step, losing its ability to do anything at all. Energy spread so thin, so evenly, that nothing can change anymore. No stars shining, no galaxies colliding, no new things forming. Just stillness. It's less like a dramatic curtain drop and more like the last candle burning all the way down, leaving only smoke and memory behind. But here's the curious part. As we sit together right now on this tiny planet orbiting a star halfway out in a galaxy that itself is just one of trillions, the idea of heat death feels both impossibly remote and oddly intimate. Because even though this scenario plays out over unfathomable spans of time, it connects to concepts we already know: entropy, energy, light fading into dark. And maybe, in its own quiet way, it tells us something about our lives here and now. Where are you listening from tonight? Are you curled up in bed, drifting off after a long day? Or perhaps lying back on the couch, earbuds in, with the world around you dimming into evening? In a way, each of us is holding our own little piece of the universe's story. And while the far future may be hard to picture, it's built on the same rules that shape the tick of the clock in your room or the warmth of a cup of tea. If you find these wanderings soothing or thought-provoking, or simply a gentle way to slow down your thoughts before sleep, I'd be grateful if you tapped the like button or maybe even subscribed. It helps this quiet space find its way to others who might need a moment of calm. And with that small gesture, we can continue this journey together, following the long arc of the cosmos wherever it leads. So let's settle in, soften the edges of thought, and begin. Picture the universe not as it is now, but as something alive with energy, buzzing with potential. Because that's where the story of heat death begins. Energy is everywhere around us. Stars blaze because nuclear reactions deep in their cores turn mass into light and heat. Galaxies shimmer because countless suns are pouring out radiation, feeding planets and warming dust clouds. On Earth, the entire dance of life is powered by sunlight falling on oceans, forests and fields. Without that flow of energy, there would be no warmth, no food, no movement, no stories. Energy is what makes things happen. And yet, energy is also slippery. It doesn't disappear, but it does spread. That's where entropy comes in, the principle that underpins the idea of heat death. Entropy is often described as disorder, but it might be more accurate to think of it as evenness. Imagine pouring milk into coffee. At first, there are swirls, patterns, little currents of difference. The coffee is doing something, changing, mixing, but eventually the milk and coffee become one uniform shade of brown. No patterns left, nothing left to mix. The system has reached equilibrium. That's entropy at work. The universe, in the grandest sense, is doing the same. Energy that starts concentrated, like in the heart of a star, eventually spreads out. The star burns its fuel, radiates its light, and after billions of years, dies. The concentrated pocket of usable energy is gone, replaced by matter and radiation dispersed into space. That radiation, once bright and hot, stretches into longer and longer wavelengths as the universe expands. Heat thins into cold. Over cosmic timescales, this process doesn't stop. It keeps going, and entropy keeps climbing. When physicists talk about heat death, they're really talking about the point at which entropy is maxed out. A state where everything is evenly spread, and because of that, nothing can happen anymore. No gradients of heat to drive engines, no clumps of matter left to collapse into stars, no fresh fuel for the cosmic fire. It's not just an end, it's the end of endings, because endings require events, and in heat death, events are no longer possible. That sounds bleak, and in many ways it is. But let's not rush there. The path to heat death is long, staggeringly long, and filled with fascinating stages. The universe doesn't just suddenly flip into stillness. It passes through ages, the stellar age, where stars like our sun burn bright, the degenerate age, when stars are gone but remnants like white dwarfs and neutron stars remain, the black hole age, where gravity rules and even the darkest giants eventually fade, and beyond that, the final age, where only the thinnest whisper of particles and radiation drift in silence. Each stage has its own story, and following that story is like walking through a museum of futures. As we wander through these possibilities, it might be helpful to remember that this isn't just an exercise in imagination. The theory of heat death arises from real physics. The laws of thermodynamics, the expansion of space, the way energy behaves. These are things we can observe here and now, scaled up to the entire cosmos. And though scientists don't claim to know the final truth with certainty, heat death remains one of the most consistent and widely accepted scenarios. Even so, there are other possibilities. Some theories suggest the universe could reverse its expansion in a big crunch. Others imagine a violent tearing apart in a big rip. Some speculate cycles of bouncing cosmos, endlessly reborn. Each has its allure, its strange logic. But tonight, our focus stays on heat death, because it's the one that feels both inevitable and oddly serene. Not fire, not chaos, but quiet. As you listen, let your thoughts drift with the scale of it. The stars above you, billions of light years away, are part of this same story. The warmth in your blanket, the hum of your body, all trace their origins to the energy released long ago when the universe was young and hot. That same energy, still moving, still spreading, will one day fade into evenness. From a blazing beginning to a whispering end, it's the same thread. And so, with that image in mind, we'll follow the universe as it unwinds, tracing the slow journey from a cosmos of light to a cosmos of stillness. When scientists speak of heat death, they are not describing flames or destruction in the way we often imagine an ending. The phrase can be misleading if you picture a world burning out in a rush of fire. It is instead about the absence of fire, the fading of heat itself until everything has cooled and evened out. To make sense of this, it helps to slow down and ask what it really means for the universe to lose its capacity to change. Energy is the currency of action. Every flicker of movement in the cosmos is powered by energy flowing from one place to another. When the sun warms your skin, it's energy moving outward. When a river turns a turbine, it's energy moving downward. When your heart beats, when an atom vibrates, when a star fuses hydrogen into helium, all of it is energy on the move. What makes energy useful, what allows it to power change, is not just its presence but its unevenness. A hot thing next to a cold thing, a compressed spring next to open space, a charged battery beside a wire. It is the difference, the imbalance, that drives motion. Now picture what happens when those differences vanish, when hot and cold are the same, when compressed and relaxed no longer contrast, when charged and neutral are indistinguishable. At that point, energy is still present, but it cannot do anything. There is no gradient to flow across, no imbalance to correct. The system has reached what physicists call maximum entropy, a condition where everything is evenly distributed and nothing more can happen. That is what heat death means at the scale of the entire universe. Imagine every star that ever burned, every galaxy that ever shone, every engine that ever ran, all of them playing their part until no useful differences remain. The energy is still there, scattered across the endless cosmos, but it is so thinly spread, so evenly balanced, that nothing new can emerge. A cosmic stillness, not because the universe ran out of stuff, but because it ran out of ways to rearrange that stuff. To appreciate why this makes sense, it helps to recall a simple rule of physics called the second law of thermodynamics. This law says that in a closed system, entropy tends to increase. You can think of it as a tendency for things to spread out, to lose their patterns, to move toward evenness. If you place an ice cube in a glass of warm water, the cube melts and the water cools until everything reaches the same temperature. The process never spontaneously reverses. You never see a glass of lukewarm water suddenly separate itself into ice and warm liquid again. The even state is stable, the uneven one unstable. The universe, taken as a whole, behaves like that glass. When it was young, right after the Big Bang, it was full of concentrated energy. Matter was clumped, radiation was intense, differences were enormous. Over billions of years, stars lit up, galaxies formed, and life emerged, all powered by the flow from those initial imbalances. But each step along the way has been a move toward more evenness. Stars burn their fuel and collapse. Radiation stretches as space expands. Matter thins out. The overall direction is always the same: higher entropy, more evenness. So when cosmologists say the universe might end in heat death, they are describing the logical endpoint of that process. A future where entropy is maximized, where no gradients remain to drive anything. It is not a violent finish, but a slow decline into equilibrium. Picture the last glow of a coal fading into the same darkness as the night around it, except scaled up to everything that exists. But the phrase can feel abstract. What does it mean in practical terms for nothing to happen? Let's consider it from familiar angles. Think about stars. They shine because nuclear fusion releases energy, driving light outward. That light can then warm planets, stir atmospheres, and nurture life. But fusion only works while fuel remains. Hydrogen fuses into helium, helium into heavier elements, until no fuel is left. At that point, the star collapses into a remnant, a white dwarf, a neutron star, or perhaps a black hole. None of those objects can radiate fresh energy in the same way. They may glow faintly for a time, but eventually they cool. Multiply this by every star in every galaxy, and you see the direction. A universe once filled with blazing suns will one day be filled only with dark remnants. Now consider black holes, the dense gravitational wells left by the collapse of massive stars or even by entire galaxies. For a long time, it seemed black holes might be eternal, swallowing matter and light forever. But Stephen Hawking showed that even black holes radiate slowly, losing energy through a process now called Hawking radiation. Over unimaginable stretches of time, even the largest black holes will evaporate, leaving only faint particles drifting outward. If even black holes cannot last, then truly nothing does. On yet another level, think about atoms themselves. Over spans of time so vast they defy intuition, even protons may decay. This is still an open question, but if it proves true, then the very building blocks of matter will not survive the march of entropy. Everything will dissolve into a sea of lighter particles and radiation, spread across an expanding universe. That is heat death. Not fire, not collapse, but dissipation. A universe that keeps expanding, growing colder, thinner, more even, until there are no stars, no black holes, perhaps not even atoms, just uniformity. A cosmic silence so complete that nothing within it could ever break it again. At first glance, it can feel hopelessly bleak. An eternal future where nothing can happen seems like the opposite of wonder. But it is also strangely elegant. The same laws of thermodynamics that explain why your coffee cools on the counter also predict the fate of the entire cosmos. The same principle that explains why your bedroom gets messy over time also describes why the universe as a whole trends towards stillness. It is the same rule, scaled from the smallest room to the largest expanse imaginable. There is a curious comfort in that consistency, the idea that the fabric of reality is stitched together by the same patterns, from the humdrum to the cosmic. When you place an ice cube in a glass, you are watching, in miniature, the principle that governs the destiny of everything. Of course, no one will be around to see the final stages. These timescales are beyond not only human lifespans, but beyond stars, planets, and galaxies themselves. The numbers are so large they lose their meaning. We can write them down, trillions upon trillions of years, but they feel more like symbols than counts. What matters is the direction, the arrow of entropy, always pointing toward equilibrium. And yet knowing this doesn't make the present less rich. If anything, it sharpens the sense that the universe is alive with temporary wonders, stars shining, galaxies colliding, planets orbiting, and life thinking about all of it. These are not permanent, but they are real. They are part of the process, part of the flow, from concentrated beginnings to dissipated endings. To live now, in this brief window when the universe is still full of differences, is to be part of the active story rather than the silent aftermath. When people first hear of heat death, they often ask why the universe couldn't somehow avoid it. Couldn't something restart the cycle? Couldn't new differences form? But the second law leaves a little room for that. In a closed system, entropy doesn't decrease on its own. The universe is, as far as we know, the ultimate closed system. There is nothing outside it to pump fresh energy in, nothing to reset the gradients once they have evened out. Once the balance is reached, it holds. This is why the word death appears in the name. It is not death in the sense of sudden loss, but death in the sense of final stillness, like the end of a heartbeat that will never start again. To understand heat death is to grasp a simple truth stretched across eternity. Energy cannot vanish, but it can lose its ability to act. The universe cannot disappear, but it can become quiet. That is what the phrase means. The end of activity, the end of contrast, the end of difference. The universe not gone, but done. Energy is the heartbeat of the universe. Without it, nothing stirs. Every star in the sky, every gust of wind on earth, every thought moving across your mind is carried by energy shifting from one form into another. To understand why the cosmos might one day slip into stillness, you have to follow energy as it makes its long farewell. Because heat death, in the end, is about the fading of energy's usefulness, its long goodbye played out over unimaginable spans of time. From the moment the universe began, energy has been everywhere. The early cosmos was a cauldron of unimaginable heat and density, where particles collided endlessly, where light itself was trapped, bouncing without escape. As the universe expanded, it cooled, and in that cooling, energy began to take new forms. Atoms formed, stars lit, galaxies swirled together. Each was a new chapter in how energy expressed itself, concentrated here, diffused there, constantly rearranging but never leaving. Because the rule is simple. Energy cannot be created or destroyed, only transformed. That is the first law of thermodynamics. But energy's transformations always carry a catch. In every exchange, some of it spreads out, becoming less organized, less available to do work. A star burning through its fuel transforms mass into light and heat, but that light races outward in every direction, scattering, cooling, stretching as space itself expands. Once it is dispersed, you cannot gather it back up in any practical way. The flow is always outward, always toward greater entropy. You can see this even in the simplest examples. Strike a match, and chemical energy in the wood transforms into flame and light. That light radiates away, most of it lost forever into the air and walls. A tiny fraction warms your hand. The rest is gone to you, spread out into the world. Run an engine and heat leaks into the environment. Eat a meal and your body captures some energy for movement, but much of it dissipates as heat. Always there is loss in the sense of usefulness, a step closer to evenness. Now, imagine that same process scaled up to the entire universe. Every star is like a match, every galaxy like an engine. Every process transforms, disperses, loses a little of its concentrated punch. Over time that adds up. The total energy remains the same, but its ability to drive change shrinks. Consider stars again, those great furnaces that have lit the cosmos for billions of years. They are engines of concentration. Deep in their cores, gravity presses hydrogen into such dense conditions that fusion ignites, releasing staggering amounts of energy. That energy streams outward, creating the light we see and the warmth that sustains planets. But stars are not eternal. They're governed by fuel. Once the hydrogen is gone, they evolve. Small stars shrink into white dwarfs. Massive ones explode and collapse into neutron stars or black holes. Each path is dramatic, but each ends the same way. No more fusion, no more fresh energy. What remains is leftover heat slowly leaking into space. Even that leaking cannot last forever. White dwarfs, for instance, will cool over trillions of years, radiating their warmth into the vastness until they reach the same temperature as the cosmic background. At that point, they become black dwarfs, cold, inert, silent. Multiply that by every star that ever lived, and you can see the trend. The night sky, once crowded with shining lights, will dim, then go dark. But energy does not vanish with the stars. It continues its slow migration outward. Radiation fills space, each photon stretching as the universe expands. What once was bright starlight becomes faint infrared. Infrared stretches into microwaves, microwaves into radio waves, until the wavelengths are so long and so weak they are practically indistinguishable from nothing at all, still present but without any capacity to warm, to stir, to shape. Black holes offer another perspective on this goodbye. For a long time, they were thought to be perfect traps, swallowing everything, letting nothing escape. But Stephen Hawking showed that even black holes are not eternal. Quantum effects at their edges allow them to radiate slowly but relentlessly. The bigger the black hole, the slower the leak, but the leak is real. Over quadrillions upon quadrillions of years, even the largest black holes will evaporate, their mass converted into radiation, their mighty pull dissolved into faint particles. In a sense, this evaporation is energy's final encore. Gravity itself, once thought to lock things forever, gives way. The densest objects in existence yield their energy to the void. When even black holes are gone, nothing remains that can create new differences, no concentrated sources left to fuel change. There are even deeper questions about the tinier scales. Protons, the building blocks of atoms, might not last forever. If they decay, as some theories suggest, then the very matter of the universe will eventually dissolve into lighter particles, neutrinos and photons drifting endlessly. This process, if real, would take timescales so immense they almost lose meaning, numbers with more zeros than you could fit in a lifetime of writing. But in the logic of entropy, even that is just another step in energy's spread. It is tempting to think of this process as sad, a kind of cosmic tragedy. But there is another way to view it. Energy's long goodbye is not a flaw in the design, it is the design. The only reason stars shine at all is because they can exhaust themselves. The only reason life can exist is because energy can flow, can transform, can spread. The universe's beauty is inseparable from its impermanence. To have sunsets, you must have stars that will someday go dark. To have warmth, you must have heat that will one day dissipate. And so the long goodbye is not just about endings, but about everything that happens along the way. Every story in the cosmos is written on this current, from galaxies forming to oceans stirring to neurons firing. All of it is energy flowing from concentrated states into spread out ones. The universe is alive with drama precisely because it is heading towards stillness. Without that direction, there would be no motion, no life, no story to tell. Imagine for a moment the stages of this goodbye unfolding. In the near future, measured in billions of years, stars like our sun will live out their lives, leaving behind faint embers. In longer spans, measured in trillions, those embers will fade, galaxies will grow dark. In even longer ages, black holes will dominate, swallowing what remains, only to slowly evaporate themselves. Beyond that, perhaps the very protons decay, leaving only a thin sea of radiation and particles. The final stage is not destruction but dilution, not chaos but equilibrium. The sheer timescales defy comprehension. The universe is already nearly 14 billion years old, yet that is nothing compared to what lies ahead. The cooling of white dwarfs alone stretches across 10 to the power of 15 years. Black hole evaporation takes 10 to the power of 100. Numbers so vast they lose connection to everyday thought. But whether or not we can hold them in mind, they remind us of a simple fact. The universe is not racing toward its end. It is strolling. Energy is not leaving in a hurry. It is bowing out slowly, gently, inevitably. And perhaps that slowness is what makes the idea less frightening. There is no sudden collapse, no violent finish, just a gradual dimming, a soft spreading, a curtain lowering one thread at a time. Energy's goodbye is long, almost infinitely long, and it is happening even now, quietly, in every transformation around us. If you feel the warmth of your blanket, that is energy dispersing. If you sip a cup of tea, that is energy flowing from liquid into you, then into the room. If you turn off a lamp, the filament cools, radiating its last glow into the night. In each case, the story is the same one writ small, a concentrated source becoming a dispersed background. The pattern repeats from the smallest corner of a room to the entire sweep of the cosmos. So when we say the universe will end in heat death, what we really mean is that this process continues without limit. Energy transforms, disperses, fades in usefulness, until eventually there are no concentrated sources left. Energy itself remains, because it cannot vanish, but the ways it can act have all been spent. It is a farewell not in a single moment, but in a slow wave that passes across all of time. This is energy's long goodbye, a story that begins in fire and ends in quiet, stretched across trillions upon trillions of years. Not sudden, not dramatic, but certain, steady and patient. And as it unfolds, it carries with it everything that ever was, every star, every planet, every life, every thought, woven into the same current. Entropy is one of those words that sounds more complicated than it really is. It sits in physics textbooks, wrapped in equations, diagrams, and technical phrasing. But the idea itself can be felt in everyday life. You've seen it when you've watched ice melt into water, when you've left your room unattended for a week and found it somehow messier than before, when you've poured milk into coffee and watched the swirls blur into a single shade of brown. These are little windows into the principle of entropy, which is the quiet rule behind why the universe moves from order to disorder, from difference to sameness, from usable energy to evenly spread stillness. Entropy doesn't mean chaos in the wild sense of the word, though that's often how it's described. It's not about everything suddenly going haywire, it's about probability. When you have a system with many parts, there are usually far more ways for those parts to be arranged evenly than there are ways to keep them neatly organised. A deck of cards shuffled will almost never return to a perfect sequence, not because it's forbidden, but because the odds are staggeringly small. A tidy desk has only one or two configurations that count as neat, but thousands that count as clutter. In physics, those odds are captured in the idea of entropy. High entropy means many possible arrangements, low entropy means only a few. In the universe, entropy is the drummer keeping time. Not a fast beat, not a loud one, but steady, relentless, and always forward. The second law of thermodynamics tells us that in a closed system, entropy tends to increase. This is why your coffee cools rather than heats itself, why perfume spreads across a room instead of clustering in one corner, why the heat from your laptop seeps into the air rather than returning to charge the battery. Energy is still conserved, but it flows into more probable, more even states, and once there, it doesn't spontaneously reverse. When cosmologists talk about heat death, entropy is the central character. Because heat death is nothing more than the moment when entropy has gone as far as it can go. When the universe has reached the state with the highest probability, the most even spread. No gradients left, no patterns remaining, just maximum entropy. At that point, the drummer has hit the final beat. To picture why entropy matters, imagine a hill with a ball resting on top. At first, the ball has potential energy. It could roll down. Push it, and it will move, converting that stored energy into motion. Once it's at the bottom, though, the story ends. The ball is stable, spread out, settled. Nothing more can happen without adding something new. Entropy is that push toward the bottom. The universe began on top of the hill, full of concentrated energy. Over billions of years, it has rolled downward, spreading into more probable states. Heat death is the bottom of the hill, not a crash, not an explosion, just a quiet resting point where the ball has nowhere else to go. What makes entropy fascinating is that it ties together scales both tiny and vast. Take your kitchen. You can put ice cubes into warm water and know, without a doubt, that the cubes will melt and the water will cool. That certainty exists because there are far more possible ways for water molecules to be jumbled together in a lukewarm mix than there are for them to be neatly separated into hot and cold. Now take the entire cosmos. Swap ice cubes for stars and water for the vacuum of space, and you see the same principle at work. Stars burn hot, pouring energy into space, until eventually everything reaches the same lukewarm equilibrium. One of the subtler aspects of entropy is that it's not just about heat, it's about information. When energy spreads, the details of how it was arranged get lost. You can't look at lukewarm water and know how many ice cubes it used to contain. You can't measure the background radiation of the universe today and perfectly reconstruct every detail of the Big Bang. The information is blurred, smeared out, diluted. Entropy, in this sense, is also the slow eraser of memory. The universe forgets its precise arrangements as it drifts toward equilibrium. This forgetfulness connects to why time feels like it has a direction. If you watch a movie of ice cubes melting, you know instinctively which way the film is running. The reverse, with cubes spontaneously forming from lukewarm water, looks absurd. That sense of direction, the arrow of time, comes from entropy. The future is the direction in which entropy increases. The past is the direction where entropy was lower. Without entropy, there would be no sense of forward. Time would have no preferred path. So when physicists call entropy the slow drummer of the universe, they mean it literally. Its steady beat sets the pace of time itself. Every tick of your clock, every swing of a pendulum, every orbit of a planet, every aging of a cell, all of them move in the direction entropy dictates. The beat is always the same. Forward, forward, forward. But the drumbeat isn't loud. You don't notice entropy in the moment-to-moment details of your day. You notice it over spans. A hot meal cooling as you talk, a body growing older across decades, a civilization leaving ruins behind. Entropy works patiently, not rushing, not skipping, but always in the same direction. And in the grandest span of all, it is the reason the universe will one day fall silent. There is a paradoxical beauty in this idea. Entropy increases, and in doing so, it makes some things possible even as it closes off others. Without entropy, stars wouldn't shine. They shine because fusion in their cores drives heat outward into the cold vacuum. Without entropy, engines wouldn't run. They run because fuel burns hot, exhaust leaves cool, and energy flows across the gap. Without entropy, life itself couldn't exist. Your body lives by maintaining a temporary pocket of low entropy, powered by food and sunlight. You export entropy into the world around you just by breathing, by moving, by existing. The same law that guarantees an eventual end is also the law that makes everything before it possible. Some scientists even suggest that entropy is why the universe feels alive with structure in the first place. Galaxies form because gravity pulls matter together, creating concentrated clumps that can then radiate heat outward. Stars ignite in those clumps, driving still more entropy as they burn. Planets form, life arises, thoughts unfold, all of it local decreases in entropy powered by larger increases elsewhere. The slow drummer sets the beat, and within that rhythm, countless patterns emerge, flourish, and fade. It's worth pausing to consider the scale of what entropy measures. Right now, the universe still has low entropy compared to what it could. Stars are blazing, galaxies are swirling, matter is still clumped together. We live in what physicists call the stelliferous era, the age of stars. Entropy is climbing, yes, but it has not yet reached its peak. There is still room for events, for gradients, for life. But over time, the climb continues. Every star that burns, every black hole that evaporates, every particle that decays, all of it nudges the universe closer to equilibrium. And yet there is no hurry in the beat. The numbers are staggering. The life of stars stretches billions of years. The cooling of remnants stretches trillions. The evaporation of black holes stretches far beyond even that. The slow drummer plays patiently, one beat at a time, indifferent to scales that overwhelm us. Sometimes people ask whether entropy could ever reverse, whether the drum might beat backward. In theory, the laws of physics allow it. If you could arrange a system in just the right improbable way, entropy could decrease. But in practice, the odds are so astronomically against it that it may as well be impossible. The drum never skips. It never stutters. The beat is steady, and it is always forward. This steadiness is what makes the concept of heat death so compelling. Because if entropy always increases, and if the universe is a closed system, then there is only one ultimate destination: maximum entropy. A universe so even that nothing remains to change. No hot against cold, no clumps against emptiness, no gradients at all. The slow drummer plays until the last beat, and then there is silence. But here in the present, the silence feels infinitely far away. We sit in a universe alive with contrasts, still humming with gradients. The stars are burning, the earth is warm, the air is full of currents, the oceans are restless and minds are active. Entropy is rising, but in the meantime it makes room for all of this. The slow drumbeat is not only an ending, it is also the rhythm of everything happening right now. So as you picture entropy, don't imagine it only as a thief of order, or a force that dooms the cosmos to stillness. Imagine it also as the drummer that gives time its rhythm, that sets the pace of stars, of life, of thought. Imagine it as both the reason there are sunsets and the reason sunsets cannot last forever. A beat that began at the dawn of the universe, that will continue across ages beyond imagining, and that will eventually carry the cosmos into silence. And in that thought, there is a curious calm, because if entropy is the drummer, then all of us, every star and planet and living thing, are simply dancing to its rhythm. Temporary, fleeting, but real. The music may end one day, but for now it plays. When you step outside on a clear night and look up, the stars seem countless. Tiny sparks, each one flickering as though it were a campfire in the distance. They feel eternal, like they have always been there and always will be. Yet stars are not permanent fixtures. their engines running on fuel, and fuel always runs out. If entropy is the drummer setting the pace of the universe, stars are the dancers, burning brightly for a time and then fading away. Their lives tell the story of energy's rise and fall, and in many ways they are the most vivid example of the long cosmic process that leads to heat death. To understand how stars fit into this story, it helps to imagine what they really are. Each star, including our Sun, is a balance between gravity pulling inward and nuclear fusion pushing outward. Gravity alone would crush the star, collapsing gas into an ever denser ball. Fusion alone would blow it apart, scattering material across space. But together, they create a balance. Gravity compresses hydrogen atoms so tightly that they fuse into helium, releasing enormous amounts of energy in the process. That energy pushes back against gravity, and for as long as the fuel lasts, the star shines. Think of it like a campfire. Logs piled together will burn, giving off light and warmth. The flames dance as long as there is wood to consume. Eventually, though, the logs are gone, and the fire dwindles to embers. The warmth fades. The smoke drifts away. Stars are much the same. They burn, they blaze, and in the end, they fade. But unlike campfires, stars come in an astonishing range of sizes and lifespans. The largest stars, many times the mass of the Sun, live fast and die young. They burn through their fuel in just a few million years, a blink compared to cosmic timescales. When their fuel is exhausted, they collapse violently, often exploding in supernovae that outshine entire galaxies for brief periods. The remains might form neutron stars, tiny but incredibly dense, or black holes, where gravity overwhelms everything. The smallest stars, on the other hand, burn slowly, steadily. Red dwarfs, cooler and dimmer than our Sun, can last trillions of years, longer than the universe itself has currently existed. They are the quiet campfires, glowing faintly but persistently, stretching their fuel across unimaginably long nights. Our Sun sits in the middle. Not too large, not too small, with a lifespan of around 10 billion years. It is roughly halfway through its life now, shining brightly, fueling the Earth, powering winds and weather, oceans and life. But it too is on a clock. In about 5 billion years, it will swell into a red giant, consuming the inner planets, including our world, before shrinking down into a white dwarf. It will cool slowly, radiating its last warmth until, eventually, it becomes cold and dark. This is not a special fate. It is the common fate of stars. The universe's great campfires are temporary. The fuel runs out, and once it does, there is no way to restart it. Fusion is a one-way road, moving hydrogen to helium, helium to heavier elements, until no further reactions can sustain the heat and pressure needed. Once a star reaches that point, its shining days are over. But while stars live, they are the engines of creation. They do more than shine. Inside their cores, elements are forged. The oxygen you breathe, the calcium in your bones, the iron in your blood. All of it was made in the heart of stars that lived and died long before our Sun was born. Every heavy atom in your body was carried here by ancient supernova, scattered across space, gathered into clouds that later formed new stars and planets. Without stars as campfires, lighting and relighting across generations, there would be no complexity, no chemistry, no life. This makes the fading of stars bitter-sweet. They are temporary, yes, but their temporary blaze gives rise to everything else. Without their burning, there would be no Earth, no oceans, no forests, no minds to wonder about the night sky. Stars are both fleeting and essential, and in their endings, they write the script of what comes next. In the context of heat death, stars are one of the earliest steps in the long goodbye. As long as they burn, energy flows from concentrated cores to the surrounding space. Entropy increases, but there are still differences to drive events. A young universe alive with stars is full of contrast, bright against dark, hot against cold, clumped against empty. But as stars die, those contrasts shrink. White dwarfs cool, red dwarfs dim, neutron stars fade. The universe grows quieter. Imagine the timeline. Right now, the universe is about 13.8 billion years old. Stars are still forming, burning, and dying. The night sky is crowded with light. But fast forward 1 trillion years, and the picture is very different. Star formation will have slowed to a trickle. Most of the bright stars will be gone, leaving only red dwarfs glowing faintly. Galaxies will still exist, but they will be darker, quieter, their great spirals less vibrant. Skip ahead even further, to 100 trillion years, and star formation will have ceased altogether. The last red dwarfs will be flickering, slowly exhausting their fuel. The campfires of the cosmos will be down to their final coals. At that point, the universe enters what physicists call the degenerate era. Stars as we know them are gone. What remains are remnants, white dwarfs, neutron stars, black holes. The sky will be filled with these quiet leftovers, no longer producing light of their own. Occasionally a remnant might collide with another, releasing a burst of energy, but these events will be rare, scattered across enormous distances. For the most part, the cosmos will be dark. The image is striking if you let yourself linger on it. A universe once filled with blazing suns, galaxies shining bright, constellations forming pictures across the sky, reduced to faint embers scattered across a growing void. Stars as flickering campfires, one by one going out. And yet, there is something almost comforting in the rhythm. Because just as campfires bring warmth and light for a while, so too do stars. They were never meant to last forever. Their impermanence is what makes them beautiful. The night sky you see today is temporary, a snapshot in a much longer story. The constellations will not always be there. The bright band of the Milky Way will not always stretch across the heavens. But for now, it does, and that makes it precious. It is easy to think of heat death as only about loss, about fading into nothingness. But if you turn the thought around, it is also about how remarkable it is that stars shine at all. For billions of years, these giant campfires have blazed, giving rise to planets, life, and wonder. They are temporary, yes, but in their temporary nature lies all the richness of the universe we know. And when the last stars do fade, it will not be a sudden end. Their light will linger, stretching across space, red-shifting as the universe expands until it blends into the background. The darkness will grow, but the fading will be slow, patient, giving time for countless other processes to play out. The long goodbye of energy continues one star at a time, so the stars flickering as campfires in the vast night are the beginning of the universe's winding down. They blaze, they fade, they pass their elements onward, and in doing so they mark the first steps toward Entropy's quiet finale. Look at them now while they are here, and you're seeing the temporary lights of a cosmos that is slowly heading toward stillness. When you look up at the night sky and see that hazy band of the Milky Way, you're really looking at your home galaxy from the inside, a vast disk of stars, gas, dust, and dark matter, stretching 100,000 light-years across, with our sun circling quietly about halfway out from the centre. It feels permanent, like the sky itself, but galaxies, like stars, are not eternal. Their future is shaped by the same rules that govern everything else: gravity, energy, and entropy. And when scientists imagine the long arc toward heat death, they also have to imagine what happens to galaxies as they slowly drift apart. At present, galaxies are still forming stars, still colliding with each other, still growing in structure. The universe is not yet quiet, but already the seeds of their fate are clear. The expansion of space, first noticed in the 1920s by Edwin Hubble, has not stopped. Distant galaxies are moving away from us, their light stretched into longer wavelengths as space itself grows between us and them. The farther away a galaxy is, the faster it recedes. It is not that galaxies are racing through space like cars on a highway. The highway itself is lengthening, carrying them apart. For a long time, it was assumed this expansion might slow down under the pull of gravity. After all, galaxies contain enormous amounts of matter. Shouldn't their combined pull at least slow the growth of space? But in the late 1990s, observations of distant supernovae showed something astonishing. The expansion is not slowing, it is accelerating. Some unknown force, called dark energy, is driving galaxies apart faster and faster. This discovery changed how we think about the fate of the cosmos. Because if expansion was slowing, gravity might one day reverse it, pulling everything back into a big crunch. Instead, acceleration means galaxies will continue drifting apart forever. Over time, they will slip away from each other, carried into isolation by the swelling fabric of space. So what does that mean for the galaxies themselves? First, it means that local groups of galaxies will stay together, bound by gravity. Our Milky Way, for example, is on a slow collision course with its neighbour, the Andromeda Galaxy. In about 4 billion years, the two will merge, forming a larger elliptical galaxy often nicknamed Milkomeda. This new galaxy will include billions of stars from both systems, their orbits stirred into new patterns. Other small galaxies in our neighbourhood will also be drawn in, creating a single massive structure. But beyond our local group, other galaxies will drift away. Already, those beyond a certain distance are receding faster than light relative to us. That doesn't mean they are breaking cosmic speed limits. It means the expansion of space between us is growing so rapidly that light from them can never reach us. In the far future, this effect will grow. One by one, distant galaxies will slip beyond our cosmic horizon. Their light will never arrive. Eventually, billions of years from now, the night sky will no longer be crowded with galaxies. Our descendants, if any still remain, will see only the stars of our own merged local galaxy. The rest of the universe will be invisible, carried away into unreachable distance. This paints a strange picture. Right now, we live in a golden age for cosmology, when we can see other galaxies, measure their redshifts and learn about the expansion of space. But in the far future, observers would not be able to see any of this. The evidence for an expanding universe would be gone, erased by the very process it revealed. The stars above them would seem isolated, the galaxy alone in darkness. Only the laws of physics, still embedded in matter and energy, would hint at the wider story. Inside the galaxies themselves, the changes unfold more slowly. Stars continue to form for a time, though eventually the gas supply dwindles. Collisions stir up bursts of new star formation, but once the fuel is used up, the process halts. After trillions of years, galaxies become graveyards of stellar remnants. White dwarfs, neutron stars and black holes orbit silently in the dark, the once bright disk gone quiet. Dark matter, the unseen mass that holds galaxies together, remains, keeping these remnants bound. But even bound systems are not immune to time. Over unimaginably long spans, gravitational encounters between objects will slowly kick some stars and remnants out of the galaxy. Others will sink toward the centre, feeding the central black hole. In the end, most galaxies will slowly evaporate, their members drifting away one by one until only black holes remain at their cores. And even those black holes are temporary. As Hawking radiation works its patient magic, the giants will shrink, then vanish. What was once a galaxy, a bright island of stars in the cosmic sea, will dissolve into a faint mist of radiation, scattered too thin to ever gather again. All of this happens against the backdrop of expansion. As galaxies fade, they are carried ever farther from one another. Isolation grows deeper. Space stretches wider. Structures that once filled the sky grow invisible. If you imagine the universe as a great campfire, galaxies are the sparks, and expansion is the breeze carrying them apart. Slowly, steadily they drift into the night, fading as they go. But in their drifting, galaxies also leave behind stories. The heavy elements forged in their stars, scattered in supernovae, become part of the fabric of planets, of life, of thought. Even as they disperse, their influence lingers. The atoms in your body were once part of ancient galaxies long gone, their light faded, their stars extinguished. In that sense, the fate of galaxies is not only about their disappearance, it is also about their contribution. They light the path to everything else, even as they fade into silence. The image of galaxies drifting apart is both lonely and beautiful. Lonely, because it suggests a future where each patch of the universe is cut off from all others, isolated in darkness. Beautiful, because it reflects the consistency of physics across all scales. This same expansion that carries galaxies apart also carries starlight into redshift, also carries heat into equilibrium. It is the same process, unfolding patiently, shaping everything from the broadest structures to the smallest particles. Right now, when you step outside and see the Milky Way, you're seeing the universe in its vibrant age, alive with galaxies, alive with light. But in the long march toward heat death, this is only a moment. The stars will fade, the galaxies will drift, and the sky will grow empty. Not suddenly, not violently, but slowly, patiently, in keeping with a steady beat of entropy. And so the fate of galaxies is sealed not by destruction, but by distance. They drift apart until they vanish from sight, until their structures dissolve, until only radiation remains. A quiet fate, carried on the currents of expansion, one more step in energy's long goodbye. If the great blue giants of the universe are its fireworks, the red dwarfs are its embers. Small, cool, and faint compared to stars like our sun, they might not look like much at first glance. In fact, with the naked eye you cannot see a single one in the night sky, even though they're by far the most common type of star in the universe. What makes them extraordinary is not their brightness, but their patience. While massive stars live for only millions of years, red dwarfs endure for trillions. They burn their fuel so slowly that they will be the last stars to shine when all others have gone dark. To understand why they are so long-lived, it helps to think about how stars use their fuel. A star is like a furnace, where gravity compresses hydrogen atoms until they fuse into helium, releasing energy in the process. The more massive the star, the stronger its gravity, and the hotter and denser its core becomes. That high pressure makes fusion rage at an astonishing rate, which is why giant stars burn through their fuel so quickly. Red dwarfs, on the other hand, are small. Their cores are cooler, their pressures lower. Fusion happens, but it happens slowly. This slow pace gives red dwarfs an advantage. They sip their fuel instead of gulping it. A massive star like Rigel or Betelgeuse blazes brilliantly but dies young, like a fire consuming logs in a furious blaze. A red dwarf is more like a coal glowing gently in the dark, giving off a steady heat without rushing. While the sun will last about 10 billion years in total, many red dwarfs are expected to endure for 10 trillion years or more. That is 1,000 times longer than the current age of the universe. What makes them even more efficient is that they are fully convective. In stars like the sun, the outer layers don't mix completely with the core, which means some of the hydrogen fuel never makes it down to where fusion occurs. A red dwarf, by contrast, stirs itself from top to bottom. Every bit of hydrogen eventually cycles through the core, ensuring almost nothing goes to waste. That is why they can shine for so long. Right now, most of the red dwarfs that will one day be the last lights of the cosmos are still young. Many are only a few billion years old, practically newborn compared to their lifespans. Long after our sun has swelled, died, and cooled into a white dwarf, these faint stars will still be burning, dotting the universe with soft red glows. When the galaxies have aged, When the skies have grown emptier, the red dwarfs will remain, quiet and persistent, like lanterns along a deserted road. Their appearance is humble. A red dwarf is smaller than the Sun, sometimes only a tenth its mass, sometimes just barely massive enough to sustain fusion at all. They shine dimly, often less than 1% as bright as our star. Up close, they can flare violently, sending bursts of radiation into space, but at a distance they are steady companions glowing softly in the dark. Planets can and do orbit them, and some scientists even speculate that life might endure around red dwarfs far longer than around stars like ours, simply because the fuel lasts so much longer. Imagine the far future, trillions of years from now, when most of the universe's stars have gone dark. The bright blue giants will be gone, long collapsed into black holes or neutron stars. The yellow suns like ours will be gone too, reduced to white dwarfs and then to black dwarfs, cooling and fading. But scattered across the dark will still be red dwarfs, faintly glowing, their light stretching across lonely galaxies. These will be the last campfires, the final sources of warmth and brightness in a universe otherwise dimming. Eventually, though, even their patience will run out. After trillions upon trillions of years, they will have used up all their hydrogen. Without fuel, they will shrink and cool, turning into white dwarfs, and from there, they too will fade. There is no escaping the path. Stars burn because fusion gives them gradients of energy to release. Once fusion ends, the gradients vanish, and entropy wins. It is strange to think that the very stars most people never notice are the ones that will write the final chapter of starlight. When future skies are dark, when galaxies are ghosts of themselves, when black holes are the last giant standing, the faint red dwarfs will still be shining. Their glow will linger, marking the last flickers of a cosmos that began in brilliance and ends in quiet embers. There is something deeply poetic about their role, though without needing to lean on poetry. They remind us that survival is not always about power, but about pacing. The largest stars may dominate the sky with their brilliance, but they are gone in an instant by cosmic standards. The smallest endure quietly, patiently, until nearly all else has passed away. If you could stand on a planet orbiting one of these red dwarfs in the far future, the night sky would not look anything like ours. The galaxies would have slipped beyond sight, carried away by expansion. The universe would be darker, emptier, quieter. But overhead your star would still shine, faint but steady, keeping time against an eternity of silence. That image, lonely as it is, also carries a strange comfort. For as long as red dwarfs glow, the universe is not yet done. And when they finally do burn their last, the cosmos will step into a new age. The age of remnants only, when no new stars are born, when only white dwarfs, neutron stars and black holes remain. But before that comes, for trillions of years the red dwarfs will keep their vigil. The last campfires of the night, flickering patiently before they too go out. When a star like our Sun runs out of fuel, it does not explode in a violent supernova. It takes a gentler path. After swelling into a red giant and casting off its outer layers, the core remains behind as a white dwarf, a dense ember about the size of Earth, but holding roughly half the Sun's mass. White dwarfs shine, but not because they are burning fuel. They shine because they are hot, radiating away the heat left over from their long lifetimes. Over billions of years they cool, slowly dimming, fading from white to red to black. When that cooling is complete, what remains is something the universe has not yet seen, a black dwarf. Black dwarfs are purely theoretical today. None exist yet because the universe is simply not old enough. White dwarfs cool incredibly slowly. Our cosmos, at 13.8 billion years, has not had the time for any to finish their cooling journey. It will take trillions upon trillions of years before the first white dwarfs fade into true darkness. But one day, far beyond any timescale we can easily grasp, black dwarfs will fill the cosmos. So what are they like? Imagine a star that once shone brightly, warming planets, nurturing life, blazing in the sky of some ancient world. Over billions of years it exhausted its fuel, shed its outer layers, collapsed into a white dwarf, and glowed faintly as it cooled. Trillions of years later, it no longer emits light. It is cold, dark, inert. A black dwarf is, in essence, a dead star, an echo of a sun that once was, its mass still present, its shape still intact, but its energy spent. To picture one, think of an object about the size of Earth, but unimaginably dense. A teaspoon of its matter would weigh tons, its gravity would still be strong, tugging on anything nearby. But it would be invisible in the dark, detectable only by its pull on surrounding objects. Silent, hidden, it would drift through space like a ghost of the star it used to be. The idea of black dwarfs is haunting, but also fascinating. They represent a stage of the universe we cannot yet observe. They are the shadows of stars, the natural end of a process that has been underway since the first suns ignited. If white dwarfs are the coals of a cosmic fire, black dwarfs are the ashes left behind when the last heat is gone. What makes them especially important in the story of heat death is their permanence. Once black dwarfs form, they will not reignite. There is no new source of fuel, no process to bring them back to life. They will simply drift, dark and silent, as the universe continues to expand and cool. For trillions of years, galaxies will fill with these remnants, each one a reminder of a time when stars blazed. But even permanence may not be absolute. Some theories suggest that over timescales so vast they defy imagination, even black dwarfs might not last forever. Protons, the building blocks of matter, may eventually decay, though this has not yet been confirmed. If proton decay is real, then black dwarfs will ultimately dissolve, turning into lighter particles and radiation. If not, they may persist indefinitely, dark monuments in a cold cosmos. There is another curious possibility. Some physicists have proposed that in unimaginably long spans of time, black dwarfs could still experience rare quantum events. Nuclear reactions that never had the chance to occur might finally take place, causing occasional bursts of energy. These events would be staggeringly infrequent, separated by numbers so large they are difficult to write down. But they suggest that even the darkest stars might not be entirely silent. A faint crackle of activity in an otherwise quiet universe. Still, those possibilities lie so far beyond comprehension that they are little more than thought experiments. What matters for us now is that black dwarfs represent the quiet end of stellar evolution. They are the final form of stars like the sun, the last stage in the long process of cooling and fading. When the cosmos is old enough for them to exist, they will mark a transition into a darker age, when light itself has become rare. The story of black dwarfs is also the story of memory. Each one is a relic, holding the shape and mass of a star that once burned. In their silence, they carry echoes of entire histories, planets warmed, elements forged, perhaps even lives that once looked up at their glow. But they themselves will not shine. They will not speak. They will only exist, reminders of what once was. If you think about the sky of that distant future, when black dwarfs have replaced stars, it is almost unimaginable. The constellations we know would be gone. The galaxies we see would be empty of light. Instead, there would be invisible masses, drifting silently, detectable only if you brushed close to their gravity. The universe would be full, but it would feel empty. The campfires extinguished, the coals gone cold, the ashes scattered across the night. Yet even in that image there is something steady, because this too is part of the pattern. Stars are born, they shine, they fade, and they leave behind their remnants. Black dwarfs are not an accident. They are the natural conclusion, the echo of suns, preserved in form if not in light. And when the last red dwarfs cool into black dwarfs, When galaxies are filled with these silent objects, the universe will step further into entropy's rhythm. Still not at the end, but closer, with one more kind of light extinguished, one more chapter of brightness closed. So as you think about black dwarfs, you can imagine them as silent markers along the universe's timeline. The echoes of suns that once filled the sky with light, now resting in darkness, waiting as the cosmos continues its slow journey toward stillness. They are reminders that nothing lasts forever, but also that even in silence, traces of what once was remain. Gravity has always been the quiet sculptor of the universe. From the very first moments after the Big Bang, it was gravity that pulled matter together, coaxing gas into clouds, clouds into stars, and stars into galaxies. Without it, there would be no structure at all, just a thin mist of particles drifting without purpose. Gravity is the reason you feel anchored to the Earth, the reason planets orbit the Sun, the reason black holes exist. And in the long future of the cosmos, as energy spreads and heat fades, gravity remains one of the last forces still shaping events. Against the slow chill of entropy, it pulls, gathers and holds, delaying the inevitable even as it cannot prevent it. In many ways, gravity is the great counterbalance to entropy. Entropy demands spreading, evenness, equilibrium. Gravity demands clumping, pulling matter into dense knots. These two tendencies play against each other constantly. A star exists because gravity pulls gas inward while energy from fusion pushes outward. A galaxy exists because gravity holds billions of stars together against their motion. Even planets and moons exist because gravity refuses to let them drift apart. In a universe without gravity, entropy would have spread everything thin from the beginning. There would be no stars to burn, no galaxies to shine, no planets to host life. Gravity created the stage on which energy's drama could play out. But gravity, like everything else, cannot escape the larger arc. It delays entropy, but it does not defeat it. Over cosmic timescales, the pull of gravity shifts from a force of creation to a force of dissolution. When stars run out of fuel, gravity takes over, collapsing them into remnants. When galaxies evolve, gravity stirs stars into new orbits, ejecting some, feeding others into black holes. Over trillions of years, gravity slowly evaporates galaxies, scattering their contents into the wider void. It works patiently, but its patience is not salvation. It only reshuffles the pieces before entropy claims them. Still, the way gravity interacts with the coming chill is worth exploring. Take stars at the end of their lives. Without gravity, their fuel would simply disperse, but gravity ensures a finale. White dwarfs form because gravity compresses the leftover core. Neutron stars form because gravity pushes protons and electrons together. Black holes form because gravity overwhelms everything, collapsing mass into a singularity. These are gravity's creations, dense, enduring, remarkable. They are the last strong structures before the universe fades. On the scale of galaxies, gravity also resists the chill for as long as it can. Galaxies are not just clouds of stars randomly moving, they are tightly bound systems where gravity balances motion. Collisions between galaxies do not tear them apart but knit them together. Our own Milky Way and Andromeda will merge because gravity demands it, reshaping their stars into a single larger system. Clusters of galaxies will also hold together, their mutual gravity binding them even as expansion carries more distant galaxies away. But this binding is temporary. Over long spans, interactions within galaxies gradually give some stars extra speed. Those stars are slingshotted outward, escaping into the void. Others drift inward, feeding central black holes or colliding with remnants. Bit by bit, galaxies lose their members until only a central black hole remains, surrounded by a faint halo of stragglers. Gravity, once the architect of grand spirals and brilliant collisions, ends up as the patient dismantler of its own creations. In the era when black holes dominate, gravity will seem like the last active force. Black holes swallow matter, bend light, warp time. They are the ultimate expression of gravitational power. For trillions upon trillions of years, they will sit at the centers of galaxies, slowly consuming whatever drifts too close. Against the backdrop of fading starlight, they will be the last giant standing, their gravity unchallenged. And yet, even black holes cannot stand forever. Hawking radiation ensures that gravity's strongest fortresses will eventually leak away, dissolving into faint particles. The very objects that seem like eternal anchors will one day be gone. Gravity, in the end, bows to the same rule as everything else. Entropy rises, gradients vanish, the chill spreads. There is something almost tragic in this story. Gravity fights tirelessly, shaping stars, forming galaxies, creating black holes, holding matter together for eons, but its victories are temporary. The chill of entropy is patient, and patience wins in the end. Still, without gravity's resistance, there would be no story at all. The universe would have begun in heat and ended in heat without ever pausing to form suns, planets, or life. Gravity gave the cosmos its structure, its beauty, its complexity. Its tug against the chill made everything in between possible. Imagine the far future when most stars are gone, when galaxies are dark. Gravity will still be working quietly, drawing remnants together. A white dwarf might spiral into a black hole. A neutron star might collide with another, releasing a final burst of light. Even as the overall direction is towards silence, gravity will stir occasional notes. Not enough to change the ending, but enough to punctuate the quiet. And so gravity's role in the universe's long goodbye is twofold. It resists entropy, creating structures, slowing the spread, giving the cosmos time to shine. And it ushers entropy forward, collapsing stars, scattering galaxies, feeding black holes. It is both builder and dismantler, both protector and executioner. In the end, its tug against the chill is not a battle it can win, but it is a dance that gave the universe its shape, its rhythm, and its fleeting brightness. In that way, gravity is perhaps the most human of the cosmic forces. It struggles, it resists, it holds on as long as it can, even knowing the end is certain. It does not prevent the chill, but it makes the time before it richer, fuller, more alive. Without it, there would be no campfires in the night sky, no galaxies drifting, no red dwarfs glowing faintly, no echoes of suns in black dwarfs. Gravity is the hand that shaped them all, and even as it surrenders, it leaves behind the universe's most lasting forms. Black holes are often imagined as hungry monsters, cosmic drains pulling in anything that drifts too close. In a way, the image is accurate. They are the densest objects in the universe, places where gravity is so strong that not even light can escape. But when you set aside the drama of that image, black holes are not violent in the way you might picture. They do not vacuum everything around them. They simply sit and wait, their gravity shaping the space nearby. If something wanders close enough, it cannot leave. And in the long, long future of the universe, when stars have faded and galaxies have dimmed, black holes will become the last great feasting giants, taking in the remnants of what once was. To understand their role, it helps to step back and remember how black holes form. When a massive star, many times heavier than the Sun, runs out of fuel, gravity wins the battle against fusion. The core collapses under its own weight, crushing protons and electrons together, forcing matter into extraordinary density. Sometimes the collapse stops at a neutron star, a sphere only a few miles across but heavier than the Sun. But if the star is massive enough, nothing can stop the collapse. It continues until the density is infinite, or at least beyond what our current physics can describe. A black hole is born. There are smaller ones, created by the collapse of stars, and there are supermassive ones, sitting at the centers of galaxies, millions or billions of times the mass of the Sun. These supermassive black holes may have formed from the merging of smaller ones, or from the collapse of giant gas clouds in the early universe. However they began, they now anchor galaxies, their gravity shaping the stars and gas around them. Our own Milky Way has one, a black hole called Sagittarius A, about 4 million times the mass of the Sun. It is quiet now, but in the past it may have blazed as it consumed matter, and one day in the future it will feed again. Black holes are patient eaters. They do not hunt, they wait. If a star drifts too close, its gravity tears the star apart, stretching it into a stream of gas. The gas spirals inward, heating up, glowing brightly before disappearing beyond the event horizon. If gas clouds approach, they too are swallowed, lighting up briefly as they fall. Even planets, asteroids, and stray bits of debris are consumed if they cross the threshold. Nothing resists once it is inside. Over time, this slow feast shapes galaxies. Stars wandering too close are eaten. Gas in the core is consumed. Remnants spiral inward. Even dark matter may be drawn toward the centre, though its behaviour is still uncertain. The central black hole grows, becoming heavier and heavier. In the far future, long after galaxies have stopped forming stars, black holes will be the most massive objects left, feeding slowly on whatever remains. But the feast is slow because the universe is vast and mostly empty. Most stars will never come close enough to a black hole to be eaten. The density of matter is too low. The black holes will wait, patient across trillions of years for occasional meals. A white dwarf here, a neutron star there, perhaps the collision of two remnants feeding the central giant. Rare events punctuate long silences. The pace is glacial, but time is on their side. This makes black holes central characters in the universe's winding down. As other sources of energy fade, they remain. While red dwarfs burn their last, while white dwarfs cool, while galaxies evaporate, black holes persist. They do not need fuel to shine, but when they do consume something, they can outshine everything else for a moment. Quasars, some of the brightest objects in the universe, are powered by supermassive black holes feasting on gas. In the future, there will still be occasional bursts, faint echoes of that brilliance, as black holes enjoy their slow banquets. But even the slowest feast has an ending. For decades, scientists thought black holes might be eternal, perfect traps that never release what they consume. Then Stephen Hawking showed that quantum mechanics changes the picture. Black holes radiate faintly, a process now called Hawking radiation. It is incredibly slow, far too faint to notice for any black hole we can observe today. But given enough time, it means black holes leak energy. They shrink, and eventually they vanish. The numbers are staggering. A black hole with the mass of the Sun would take 10 to the power of 67 years to evaporate. A supermassive one, with billions of solar masses, would take up to 10 to the power of 100 years. These numbers are so large they stretch beyond comprehension. But time is not in short supply. The universe will last long enough. Black holes will dominate the cosmos for longer than stars ever did, longer than galaxies existed in their vibrant forms. They will be the last feasting giants, and then, slowly, they too will fade. Imagine the universe in that distant future. The stars are gone, the galaxies are quiet. Black dwarfs drift in silence, and in the centres of galaxies black holes wait, massive and dark. Occasionally something wanders close, a remnant star or a loose bit of matter, and the black hole eats. For a brief time the surroundings glow as matter falls inward, releasing energy. Then silence returns. Across the dark cosmos, these rare feasts are the last events, the last flickers of activity. And then, over unimaginable spans, even the black holes themselves shrink, radiating away into nothingness. The idea of black holes fading is both unsettling and comforting. Unsettling because they seem so eternal, so absolute. Comforting because it means that nothing, not even the most powerful objects in the cosmos, escapes the same law. Entropy always rises, energy always spreads, even black holes cannot resist forever. Their slow feast, then, is less about hunger and more about inevitability. They are the final stage of gravity's work, the last collectors of matter, the last great structures. They resist the chill as long as they can, holding on to mass, devouring what comes near, but the chill is patient and in the end it wins. In the long arc toward heat death, black holes are milestones. They mark the era after stars but before silence. They are the custodians of the universe's mass, holding it for a time before releasing it back as radiation. They are not villains, not monsters, but participants in the same unfolding story, bound by the same rules as everything else. When you think of black holes in this way, the image shifts. They are not cosmic horrors, but cosmic caretakers, keeping matter together for eons, releasing it only when the time is right. Their slowest feast is the universe's way of stretching out the story, giving time for every possibility to play out before the curtain falls. And when their feast ends, when even the black holes have gone, the universe will be left with only faint whispers of radiation, spread so thin it barely exists at all. The slowest eaters will have finished, and the table will be empty. Black holes are famous for swallowing light, for pulling everything past their horizons and letting nothing escape. For a long time, that was the end of the story. Once something crossed into a black hole, it was gone forever, trapped beyond reach. Black holes were thought to be perfectly black, perfectly silent, eternal guardians of whatever they consumed. But then, in the 1970s, Stephen Hawking showed that the story is not quite so simple. Black holes are not perfectly black. They are not completely silent. They whisper, slowly, faintly, shedding energy in a process now called Hawking radiation. The discovery was surprising because it combined two pillars of physics that don't often work together smoothly: general relativity and quantum mechanics. General relativity describes gravity as the warping of space and time. Quantum mechanics describes the jittery behavior of particles and fields at the smallest scales. Usually these two theories live in separate worlds, each ruling their own domain. Black holes, however, sit at the intersection. Their intense gravity bends space so steeply that quantum effects become unavoidable. Hawking showed that when you take both theories seriously, black holes must radiate. To picture how this happens, imagine the vacuum of space not as empty, but as alive with activity. Quantum physics tells us that particles and antiparticles constantly appear and vanish in pairs, borrowing energy from nothingness before cancelling each other out again. These pairs are usually invisible, their lifetime's too short to notice. But near the edge of a black hole, the event horizon, something unusual can occur. One particle might fall inside while the other escapes. If that happens, the escaping particle becomes real, carrying energy away. To conserve energy, the black hole loses a tiny bit of mass. Slowly, patiently, it shrinks. The radiation produced this way is unimaginably faint. For a black hole the size of a star, the temperature of the radiation is colder than the cosmic microwave background, the leftover glow from the Big Bang. That means black holes we see today are actually absorbing more heat from the universe than they emit. Only when the cosmos grows colder, trillions of years in the future, will Hawking radiation start to dominate. From then on, the process continues relentlessly, until the black hole evaporates entirely. The timescales are mind-bending. A black hole the mass of the Sun would take about 10 to the power of 67 years to vanish. That is a 1 followed by 67 zeros, a number so vast it makes the current age of the universe look like an instant. For supermassive black holes, the ones at the centres of galaxies, the numbers grow even larger, up to 10 to the power of 100 years. Nothing else lasts so long. For most of the universe's future, black holes will be the dominant players, fading so slowly that they seem eternal. But they are not. The whisper of Hawking radiation ensures that even the most powerful objects cannot escape entropy's pull. What does this radiation look like? Not like the bright light of stars, not like the searing energy of a supernova. It is subtle, a trickle of photons and particles streaming away. You would not see it with your eyes, Even if you were impossibly close, it is more like heat from a stone, radiating quietly, steady and patient. But across immense times, that quiet whisper adds up. Bit by bit, mass turns to radiation. Bit by bit, the black hole shrinks. The image of a black hole evaporating is strange because it flips our usual picture. Black holes are imagined as permanent, as the ultimate endpoints, as traps from which nothing returns. To learn that they leak, that they glow faintly, that they are not eternal, is to see them in a new light. They are not exceptions to the rules of the universe. They are bound by the same principles as everything else. Energy spreads, entropy rises. Even the darkest giants must give way. In the distant future, when stars are gone and galaxies have dimmed, Hawking radiation will be one of the last sources of activity. Across the dark universe, black holes will glow faintly in this radiation, their whispers of light the only signal in the silence. They will be like fading embers, cooling so slowly that they persist for eons. And then, when their time comes, they will flare briefly in a final burst, releasing their last energy before disappearing. The cosmos will move on without them, one more step closer to equilibrium. This process is not just important for the fate of black holes. It also matters for the fate of the universe itself. If black holes were eternal, the cosmos might always contain some structure, some gravitational anchors, even after everything else had gone. But Hawking radiation says otherwise. Nothing is eternal. No object can last forever. In the logic of heat death, this makes sense. Entropy demands that everything ends in evenness. Black holes are not exempt. Their whispers of light are the guarantee. Hawking radiation also raises deep questions about information. If a black hole swallows matter, what happens to the information about what it swallowed? For years, this was an open paradox. Does the information vanish, violating quantum mechanics? Or does it somehow escape, encoded in the radiation? The debate continues, and while progress has been made, the details remain uncertain. What matters here is the larger point. Hawking radiation is not just about energy. It is about knowledge, about memory, about whether the universe forgets or remembers. The whispers of light may carry not only heat, but the faint traces of everything that ever fell inside. The idea that the universe's far future will be marked by these whispers is both eerie and calming. Imagine a cosmos with no stars, no galaxies, only the faint radiation of black holes slowly evaporating. The light is not bright, it is not warm, but it is something. A faint hum in the silence, a reminder that activity has not yet completely ceased. For ages upon ages, these whispers will be the last lullabies of the cosmos. And then, one by one, the black holes will vanish, their whispers will fade, and the universe will take another step towards silence. Hawking radiation shows us that endings are not abrupt but patient. The universe does not collapse in fire, it fades, gently, slowly, in processes so subtle they are almost imperceptible. Even the mightier structures obey the same law, losing their energy bit by bit, spreading it into the void. The whisper of light is the final echo of gravity's greatest creation, a faint signal that nothing, not even black holes, is forever. And in that whisper, you can hear the rhythm of the cosmos itself, quiet, patient, inevitable. A lullaby that carries the universe ever closer to stillness. When you think about the universe, it is hard not to imagine black holes as permanent. They seem like the ultimate survivors, the endpoint of stars, the anchors of galaxies, the deepest wells of gravity. They swallow light, hold on to mass, and bend time itself around them. For much of the cosmos's history, they are the last great structures, outlasting stars, galaxies, and most everything else. But even black holes, the giants that sit at the heart of the cosmic story, are not eternal. Slowly, patiently, over spans so vast they almost slip beyond comprehension, even black holes will vanish. The idea feels almost impossible at first. A black hole is defined by the event horizon, the boundary from which nothing can escape. Light cannot cross outward, time seems to stop at the edge, and matter is trapped forever once it falls inside. To say that something so absolute will one day evaporate seems to contradict the very idea. Yet Hawking radiation shows us otherwise. Black holes leak, they radiate faintly, shedding mass as energy. And once the process begins in earnest, the outcome is inevitable. The evaporation of black holes is slow beyond measure. Right now, the universe is far too young for the process to matter. The cosmic microwave background, the leftover glow of the Big Bang, is warmer than the radiation black holes produce. That means they absorb more than they emit. But as the universe expands, that background cools. Eventually black holes will become warmer than their surroundings and they will start to lose mass. From that moment on, the slow decline begins. For a black hole the size of the Sun, the timescale for this evaporation is 10 to the power of 67 years. That is a number so large it is almost meaningless in human terms. To put it in perspective, the universe is not yet 14 billion years old. A billion is just 10 to the power of 9. 67 is a gulf beyond imagining. For supermassive black holes, the kind at the centres of galaxies, the numbers are even larger. Some will take 10 to the power of 100 years to disappear. Compared to those spans, everything else in the universe happens in an instant. As they shrink, black holes do not fade quietly at first. For most of their long lives, the process is slow, a trickle of particles radiating outward. But as they become smaller, they heat up, and the radiation grows stronger. In their final moments, they release a burst of energy, a flare so intense it would outshine stars if stars still existed. Then they're gone, leaving nothing behind but radiation spread across the void. What is remarkable about this process is that it completes entropy's work. Black holes are the last strongholds of concentrated energy, the densest clumps of mass the universe can create. As long as they exist, there is still a difference, still a gradient. But when they vanish, even that last concentration dissolves. The energy they release is dispersed, spread thin by expansion, blended into the background. No gradients remain, no structures survive. The universe takes another step towards stillness. Imagine what the cosmos will look like in that era. The stars are gone, the galaxies dark. Black dwarfs drift silently. Neutron stars have cooled. Matter has decayed into lighter particles. And in the centres of what used to be galaxies, black holes sit alone, massive and silent, waiting. For eons they are the dominant players, the only significant structures left. But across unimaginable spans they too begin to shrink. One by one they fade into radiation. The last bursts of light in the universe are not from stars, but from dying black holes. These final moments are spread so far apart that they are less like an event and more like a long whisper. A black hole evaporates here, another there, separated by numbers so vast they defy intuition. There will be no grand finale, no synchronized ending, just a slow, staggered fade, until the last black hole disappears and the universe is left with nothing but thin radiation. The disappearance of black holes also raises questions about what happens to the information they once held. Every particle, every bit of matter that fell into them, is that information gone forever? Or does it somehow escape in the radiation? Physicists still debate the answer, and while some progress has been made toward resolving the paradox, it remains a reminder of how much we do not yet know. The fate of information itself may be tied to these final moments, written in the whispers of energy as black holes vanish. But from the perspective of the universe's long arc, the details of information matter less than the larger truth. Black holes, once thought eternal, are temporary. They last for longer than anything else, but not forever. Entropy always wins. Energy always spreads. The end is silence. There is something deeply calming in this vision, not because it is cheerful, it is not. The thought of every star gone, every galaxy dark, every black hole vanished, leaves the universe stripped of all structure. But there is peace in the patience of it. The cosmos does not rush, it does not collapse in fire. It fades slowly, gently, over spans so vast they become almost abstract. Even the greatest giants bow out quietly, with whispers of radiation that stretch into the void. When even black holes vanish, the universe will be in its final age. No stars, no galaxies, no remnants, only thin radiation spread evenly with no differences left to drive events. This is heat death, the ultimate equilibrium, the silence after all motion has ended, the last stage of a story that began in brilliance and ends in stillness. And yet, even here there is perspective. There is the very fact that we can imagine this future, that we can trace the laws of physics so far forward, is remarkable. From the warmth of Earth, from the vantage point of a planet orbiting a middle-aged star, we can look ahead and see the eventual fate of black holes themselves. It is not a story of hope or despair, but of inevitability, of patience, of the quiet rhythm of entropy carrying everything forward. The image of the last black hole vanishing is not the end of the story we know, it is the end of stories altogether. No observers remain to witness it, no records remain to describe it. It is simply what happens when the laws of physics run their course. The final step in a universe that always favoured spreading over clumping, stillness over motion, silence over sound. And so, when even black holes vanish, the universe is left with nothing but equilibrium. No giants to resist the chill, no structures to reshape the void. Only radiation, thin and even, carrying the faint memory of everything that ever was. Picture the universe long after the last black holes have vanished. The great engines of light are gone, the galaxies are gone, even the densest remnants of stars have dissolved. What remains is not nothing, but it is close enough to feel like it. A thin wash of radiation spreads across space, faint and even, stretched by expansion into wavelengths so long they are indistinguishable from silence. The cosmos is not empty, but it is without contrast, without events. It has become a place of darkness and ashes. The phrase might sound dramatic, but in truth it is quiet, almost gentle. Darkness, because there are no stars left to shine, no galaxies glowing in the distance. Ashes, because the black dwarfs, neutron stars, and black holes that once represented the echoes of suns and galaxies are gone, reduced to their final traces. The universe has not been destroyed in a violent blaze. It has simply faded, like a campfire that has burned all its fuel and left only cool embers behind. This age, sometimes called the Dark Era, is the culmination of entropy's patient work. Every gradient has been erased. Every pocket of concentrated energy has been spent. The spread is complete, the balance reached. Where once there were brilliant structures, galaxies spiraling with billions of stars, nebulae glowing with colour, clusters bound together by gravity, there is now only homogeneity. The universe has achieved its most probable state, its maximum entropy. To imagine what it looks like is to confront something almost alien. Our world is built on contrasts, day and night, hot and cold, light and dark, activity and rest. The universe in its dark era has none of these. There are no bright spots to punctuate the void, no heat against cold, no pockets of matter against space. Everything is even. You could travel for trillions of light years and find nothing different. Just the same thin radiation, the same stretched wavelengths, the same silence. And yet, there is still something there. Energy has not disappeared. It cannot. The law of conservation ensures that the total energy of the cosmos remains the same. What has changed is its usefulness. No part of it can be harnessed to do work because it is spread too evenly. Like lukewarm water in a glass, it is balanced, incapable of further change. That balance is what makes it ashes, not gone, but spent. Think of it as the final stage of fire. When wood burns, it releases heat and light, transforming chemical bonds into energy that radiates outward. The flames dance, the coals glow, and then, slowly, the fire dies. What is left is ash, material still present, but with nothing left to give. The universe in its dark era is ash on a cosmic scale. It has burned brilliantly for billions of years, flaring with stars and galaxies, glowing with black holes and radiation. But the fuel is gone, and what remains is inert. The silence of this future is profound. Right now, the universe is alive with noise if you know how to listen. Stars crackle with fusion, releasing photons by the countless trillions. Pulsars beam radio waves in steady rhythms. Quasars roar as black holes consume gas. Even the microwave background hums faintly, a relic of the Big Bang itself. Instruments can pick up all of these signals, showing us that the cosmos is still full of activity. But in the era of darkness and ashes, those signals will be gone. There will be no pulsars, no quasars, no stars. The microwave background will have stretched into oblivion. Only the faintest radiation spread evenly will remain, a whisper too soft to carry meaning. This raises an odd question. Can we even call it a universe at that point? Without structure, without contrast, without events, it becomes less a place and more a state. A state of stillness, a condition of uniformity. The word universe usually conjures images of galaxies, planets, nebulae, and stars. But in the dark era, those are only memories. The reality is a sea of sameness, stretching without feature, without change. From one perspective, this is the bleakest possible vision. All the beauty that ever existed is gone. No light in the sky, no planets orbiting suns, no life to wonder or dream. Only darkness, only ashes, only silence. The grandeur of the cosmos has dissolved into equilibrium. It is, in a sense, the death of possibility, but from another perspective, it is simply the natural outcome of the laws that have always ruled. The second law of thermodynamics has been at work since the beginning, increasing entropy step by step. The dark era is simply its conclusion. It is not tragedy, not disaster, but inevitability. The universe does not end in violence, it ends in balance. And there is a strange elegance in that. The same rules that explain why coffee cools, why ice melts, why fires burn, also explain why galaxies fade and why black holes vanish. The same principle that gives time its arrow carries the cosmos into stillness. From the smallest scale to the largest, it is consistent. The dark era is not an exception. It is the rule, fulfilled. If you could somehow exist in that future, what would you experience? Nothing in the sense we know it. No light to see, no sound to hear, no heat to feel. Radiation would still be present, but stretched into wavelengths so long they would be undetectable by any familiar senses. Space itself would be vast, empty, silent. The concept of distance would lose its meaning, because there would be nothing to measure between, only the void, filled with ashes too faint to notice. And yet, even here, the memory of what came before is carried in the radiation itself. The faint photons drifting endlessly are the final echoes of everything that ever was. The starlight, the supernovae, the black holes, all of it transformed into this thin background. The universe has not forgotten. It has simply blurred everything into sameness. In the story of heat-death, this is the closing act. Not sudden, not dramatic, but patient, inevitable, and absolute. The universe, once a blaze of energy and structure, has cooled into darkness. Once a stage for galaxies and stars, it has become ashes. Once alive with activity, it has become silent, and so the cosmos rests. Time is one of the most familiar things in our lives, and at the same time one of the strangest. You measure it with clocks, you feel it in your heartbeat, you see it in the rising and setting of the sun. Every story you have ever lived unfolded in time. But what happens when the universe reaches an age where nothing changes anymore? When heat death has erased all gradients, when all energy has been spread evenly, when even black holes have vanished into whispers of radiation, what does time mean then? If there are no events, no motion, no differences, is there still time? The question is not just philosophical. Physics ties the arrow of time directly to entropy. The future is the direction in which entropy increases. The past is the direction where entropy was lower. You know which way a movie is playing because you see entropy climbing. A cup of coffee cools, never warms. A building crumbles, never reassembles. Ice melts, never unmelts. Entropy provides the flow that defines before and after. But in the era after heat death, entropy has nowhere left to go. It has reached its maximum. Every difference has been erased. Every process is completed. No gradients remain to drive change. In such a state, the arrow of time loses its meaning. There is no direction because there is no change. Imagine standing in a place where nothing ever happens. No sun rising or setting, no seasons shifting, no clocks ticking, no aging, no motion. How would you sense time passing? Without events to mark it, without change to count, time becomes invisible. It might as well not exist at all. In physics, time is usually treated as another dimension, like space. You can move forward in time the way you move forward in space, but the sense of its flow is bound to entropy. Without entropy increasing, time does not feel like time. It becomes just another coordinate without meaning, without texture. In a universe of maximum entropy, time is still there mathematically, but experientially it is gone. The universe does not tick forward. It simply exists in a state of stillness. This is difficult to picture because every part of your life has been filled with change. Your body changes, your thoughts change, the world around you changes, even mountains erode, rivers shift, stars evolve. The idea of a cosmos with no change at all is so alien that it is almost impossible to grasp. It is like asking what sound is in a world with no ears, or what colour is in a world with no eyes. Time without events is time without meaning. And yet this is where the universe is headed. The gradual fade of energy, the slow evaporation of black holes, the stretching of radiation into thinness, all of it tends toward this end state. Once it is reached, the universe will not stop existing. It will simply stop changing. And without change, time itself loses its significance. There is a strange comfort in this idea. Time, which so often feels like an enemy, always moving forward, always carrying you into the future, always erasing the present, is not eternal either. Just as stars fade and galaxies dissolve, time's arrow fades too. In the far, far future, the universe itself will be free of time, not because it has vanished, but because it no longer matters. Think about how you mark time now. A second is defined by the oscillation of atoms. A year is defined by Earth's orbit around the Sun. History is measured by the rise and fall of civilizations. Personal time is marked by birthdays, memories, milestones. All of these require change. They require events. Without them, time becomes unmeasurable. You could write down numbers, but they would not correspond to anything happening. This is the fate of the dark universe. Without stars or planets, without movement or growth, without entropy increasing, there is nothing left to measure. Time may still stretch onward in theory, but in practice, it is irrelevant. The universe is timeless not because it is gone, but because nothing distinguishes one moment from the next. To put it another way, time after heat death is like a book with only one page. You can flip the page forward or backward, but it is always the same. There is no story to tell, no sequence to follow. The book exists, but it is silent. This raises deep questions about the nature of time itself. Is time something that exists independently, or is it just a measure of change? If it exists independently, then the dark universe still has time, stretching endlessly without events. If it is only a measure of change, then time itself has ended, because there is nothing left to measure. Physics does not yet have a final answer. Both views have merit, and both challenge us to think beyond our ordinary experience. Whichever view is correct, the effect is the same. From the perspective of experience, the dark universe is timeless. Nothing happens, nothing changes, nothing distinguishes one moment from another. Time without events is indistinguishable from no time at all. It is worth reflecting that this ultimate stillness stands in stark contrast to the universe's beginning. At the Big Bang, everything was happening at once. Matter, energy, space, and time erupted together in a burst of change. Entropy was low, and so time had a strong direction. Every moment was distinct from the one before, every step a surge of change. From that point forward, the arrow of time carried the cosmos through stars and galaxies, through life and thought, through all the stories we know. And at the other end, the arrow fades into silence. The contrast between beginning and end could not be greater. In one sense, this makes the present all the more meaningful. Right now, time still has direction. Entropy is still increasing. Events still unfold. Stars rise and fall. Planets turn. Life lives and dies. History marches forward. These are temporary, fleeting, but they are real. They are part of the universe's active age, the age when time matters. To live now is to exist in the window between timeless stillness at the beginning and timeless stillness at the end. Time without events is not frightening once you see it this way. It is simply the natural conclusion of a process that has always been underway. The arrow of time has been pointing in the same direction since the beginning, and once entropy is maximized, the arrow stops. Time rests. The universe rests. And perhaps that is the most calming image of all. Not destruction, not chaos, not catastrophe, just quiet, just stillness, just timelessness. A universe at peace, with no events left to unfold, no stories left to tell. Time itself has gone to sleep. When people first hear about the heat death of the universe, the reaction is rarely neutral. Some feel a wave of sadness, as if the very idea of the cosmos growing cold and silent is too heavy to carry. Others feel awe, impressed that humans can look so far into the future and imagine what might happen long after everything familiar is gone. And some feel something quieter, a strange calm, as if the vision of an inevitable stillness makes the troubles of daily life smaller and easier to bear. Whatever the reaction, it is deeply human. Because imagining the end of the universe is not just about physics, it is also about psychology. The human mind is not naturally built to handle timescales of trillions or quadrillions of years. Your life is measured in decades, your culture is measured in centuries. Even history, which stretches thousands of years, is a thin layer compared to the age of the cosmos. When you try to imagine 10 to the power of 100 years, the numbers dissolve into abstraction. They become symbols more than quantities, placeholders for longer than I can really think about. And yet, we try. Because to imagine the end of the universe is to stretch the mind to its farthest limits, to see what happens when you push thought against infinity. For many, the immediate response is existential unease. If the universe will one day fade into silence, what does that say about the meaning of life now? If everything ends in heat death, does anything matter? This feeling echoes through literature, philosophy, and even casual conversations about space. The thought of ultimate stillness can feel like a shadow falling over the present, draining it of significance. Why build? Why create? Why hope, if the cosmos itself is destined for ashes? But this unease is not the only possible reaction. Some people find the opposite, a sense of liberation. If the universe itself is impermanent, then perhaps permanence was never the point. Meaning is not found in lasting forever, but in existing at all. The stars shine not because they are eternal, but because they burn while they can. Life has value not because it avoids an ending, but because it dances before the ending comes. In this view, the thought of cosmic heat death does not diminish meaning. It reframes it. It shows that meaning is something we create in the moment, not something guaranteed by eternity. Psychologists who study how people think about mortality have noticed a similar pattern. When confronted with the inevitability of death, some retreat into fear, while others find renewed appreciation for life. The same logic extends to the universe as a whole. To imagine its death is, in a way, to imagine our own on a grand scale. It forces us to look at impermanence directly and decide how we will live in light of it. There is also something soothing about the nature of heat death itself. Other cosmic endings like the Big Rip or the Big Crunch involve violence. Galaxies torn apart, space collapsing, stars destroyed in a rush. Heat death is gentler. No explosions, no tearing. Just a gradual fading, a patient drift towards stillness. Psychologically, that image is easier to hold. It is not a universe punished or shattered, but a universe resting after a long and brilliant life. The word death in the phrase may sound harsh, but the reality is closer to sleep. This gentle quality can help explain why so many people use cosmology as a way to find calm. Lying in bed, listening to the story of the universe's end, the scale itself becomes a comfort. Your worries, your stresses, your anxieties shrink against the backdrop of trillions of years. Whatever weighs on you now is temporary, tiny compared to the vastness. The thought of eventual stillness turns into a lullaby, a reminder that everything passes and that passing is natural. Another aspect of psychology at play is our tendency to anthropomorphize, to see the universe as if it were a living being. When you hear heat death, you may imagine the cosmos as a body finally resting after exertion. The stars were its eyes, the galaxies its limbs, the black holes its heart. Now it lies down in quiet. This metaphor is not scientific, but it is deeply human. We understand the unknown by relating it to ourselves. By imagining the universe as a living thing, its end feels familiar, something we can emotionally process rather than an abstract equation on a page. There is also the role of curiosity. Humans are natural storytellers, always asking what happens next. When you hear that stars will fade, the next question is what comes after. When you hear that galaxies will vanish, you wonder what follows that. Imagining the end of the universe satisfies this instinct in the most extreme way. It is the ultimate what happens next, carried out until there is nothing more to ask. Psychologically, this gives closure, even if it is not a closure filled with hope. The story has an ending, and endings, even bleak ones, can be satisfying. Some people also find creativity in this vision. Writers, artists, and thinkers use the heat death scenario as inspiration. The idea of a cosmos grown cold, of the last stars flickering out, of black holes evaporating, sparks images that are haunting but beautiful. Art thrives on contrast, and the contrast between the vibrant present universe and the silent future provides a powerful canvas. Psychologically, this allows people to transform fear into expression, turning unease into beauty. There is even a meditative quality to imagining heat death. To picture the silence, the darkness, the stillness, is to step outside the rush of ordinary thought. It is like imagining a place beyond distraction, beyond urgency, beyond motion. Some people find peace in this, treating the vision not as despair but as a mental resting place. A reminder that the cosmos does not need to hurry, and neither do we. At the same time, there is no single correct response. Some will always feel dread at the thought of ultimate silence. Others will feel comfort. Both reactions are human, both valid. What matters is that the very act of imagining stretches us. It forces us to step outside the familiar and face scales of time and change that dwarf us. Whether you find calm or unease, the process expands your perspective. And perhaps that is the most important psychological effect of all. Thinking about the end of the universe does not change the outcome. The cosmos will move toward entropy regardless of how we feel, but it does change us. It places our lives in context. It reminds us that we are fleeting sparks in a vast story. It encourages humility, wonder, and perhaps gratitude. Gratitude that we exist in the luminous middle, in an age when stars still shine and galaxies still glow, in the brief window when the universe is alive with light. So the psychology of imagining the end is not just about sadness or awe. It is about perspective. It is about learning to live fully in the moment, knowing the moment is temporary. It is about turning the inevitability of stillness into a source of calm rather than fear. And in that way, thinking about heat death does not diminish life. It enhances it. It reminds us that meaning is not in eternity, but in the fragile, fleeting beauty of now. Heat death is the most widely accepted vision of the universe's ultimate fate, but it is not the only possibility that scientists have considered. Cosmology, like all sciences, is built on evidence, but it also relies on imagination. To study the end of the universe is to ask questions that stretch our understanding to its limits. Over the years, researchers have proposed several alternative scenarios, each one grounded in physics but shaped by different assumptions about dark energy, matter, and the laws that govern the cosmos. Among these alternatives are three of the most discussed: the Big Rip, the Big Crunch, and the idea of a cosmic bounce. Each of these possibilities paints a very different picture. Heat death is a slow fading, a gentle slide into equilibrium. The Big Rip is more violent, tearing the very fabric of space apart. The Big Crunch is a reversal, the cosmos collapsing back into itself. And the bounce is a cycle, where endings become beginnings, and the universe may repeat itself endlessly. To explore these alternatives is not just to speculate about physics, but also to reflect on the many ways humans imagine endings. The Big Rip begins with dark energy. Right now, we know that the expansion of the universe is accelerating. Galaxies are moving away from one another faster and faster, carried by something we call dark energy, a force that makes up most of the cosmos but remains mysterious in nature. If dark energy remains constant, the acceleration continues but not explosively. Galaxies drift apart more and more, but stars, planets, and atoms remain intact. Heat death follows. But what if dark energy grows stronger over time? What if its effect on expansion increases without limit? In that case, acceleration would not just separate galaxies, it would eventually tear galaxies themselves apart, then stars, then planets, then even the bonds that hold atoms together. Expansion would become so extreme that no force, not even gravity or electromagnetism, could resist. Everything would be stretched beyond recognition. In this vision, the universe ends not in silence but in shredding. Galaxies dissolve, stars are torn from planets, molecules are ripped apart, the very fabric of space-time fractures. The Big Rip, if it occurs, would arrive in a finite future, perhaps tens of billions of years from now, depending on the details of dark energy. Unlike heat death, which stretches across unimaginable spans, the Big Rip is abrupt, a final tearing, sudden and catastrophic. For some, this idea is unsettling because of its violence. For others, it is oddly comforting because it provides a clear, decisive ending. No endless waiting, no infinite fade, just a final moment when everything is undone. Psychologically, it resonates with the human tendency to imagine endings as climaxes, not fades. Whether it is likely or not depends entirely on dark energy, and at present evidence suggests dark energy is constant. Still, the possibility remains open. The Big Crunch is in many ways the opposite vision. Instead of expansion continuing forever, imagine that gravity eventually overcomes it. Matter pulls back on itself, slowing the growth of space. Expansion halts. Then it reverses. Galaxies draw closer, clusters collapse inward, stars and planets fall together. The universe contracts, growing denser and hotter until it ends in a fiery collapse. This scenario once seemed plausible before the discovery of accelerating expansion. If the universe contained enough matter, its gravity might have been strong enough to stop expansion and pull everything back. The Big Crunch would then mirror the Big Bang in reverse, a cosmic bookend. Some versions of the idea even suggested a cycle. The universe expands, contracts, and expands again, forever. The image of a big crunch is dramatic. Instead of fading, the cosmos ends in fire. Structures that took billions of years to form are undone in a rush of collapse. Temperatures soar, matter compresses, time and space themselves curl inward. In its final instant, the universe becomes a singularity again, perhaps setting the stage for another beginning. Today, the evidence for accelerating expansion makes the Big Crunch unlikely. There does not seem to be enough matter to reverse the trend. Dark energy pushes outward too strongly. Still, the concept remains important because it connects endings to beginnings. A crunch is not just finality. It may be renewal. This idea of renewal is central to the third alternative, the bounce. In this picture, the universe does not end at all. Instead, it cycles. Expansion slows and reverses, or perhaps quantum effects trigger a rebound. A new Big Bang follows the collapse and the process begins again. The cosmos becomes eternal, not in the sense of lasting in one form forever, but in the sense of repeating endlessly. Expansion, contraction, birth, death, rebirth. The bounce has appeal because it avoids the finality of heat death, or the violence of the rip. It suggests continuity, a cosmos that never truly ends but reshapes itself again and again. It also resonates with human mythologies. Many cultures have imagined the universe as cyclical, rising and falling like seasons, like tides. A bounce is the scientific echo of those ancient intuitions. Physically, whether a bounce is possible depends on unknowns in quantum gravity, the still mysterious theory that should unite quantum mechanics and general relativity. Some proposals suggest that at extremely high densities, space and time themselves might resist collapsing into a singularity. Instead, they rebound. Others imagine that black holes might seed new universes, each one a bounce into a fresh cosmos. None of these ideas are confirmed, but they remain part of the conversation, reminders that physics is still incomplete. Each of these alternative endings, rip, crunch, bounce, highlights how much remains uncertain. Heat death fits best with current evidence, but it is not the only path. The future of the cosmos depends on the exact nature of dark energy, on the fate of matter, on the laws that govern extremes we cannot yet test. In this sense, the end of the universe is not just a scientific prediction, it is also an open mystery. Psychologically, the variety of these scenarios shows something about us. We are drawn to endings that match our intuitions. Some prefer the drama of a rip, others the symmetry of a crunch, others the comfort of a bounce. Heat death, with its slow fade, feels strange because it lacks climax. It does not give the narrative punch we often expect. Yet the universe is not bound to our preferences. It will follow the laws of physics, whether or not the story satisfies us. And that too is a reminder of humility. We live in a small corner of the cosmos, for a brief time in its long history. To even imagine these endings is extraordinary. To speculate about rips, crunches, or bounces is to stretch human thought beyond its natural scales. Whatever the true ending may be, the act of imagining connects us to the universe in a profound way. So while heat death may be the leading theory, the alternatives remain important. They show us that the cosmos could surprise us, that its destiny is not yet fully written, that mystery is still alive even in the farthest future. And they remind us that endings, like beginnings, are places where science and imagination meet. Among the many possible endings the universe might face, heat death stands apart. The Big Rip, the Big Crunch, and the Bounce are fascinating alternatives, each with their own compelling images and implications. But when cosmologists weigh the evidence, they keep returning to the same conclusion. The universe is headed toward a slow fading rather than a sudden tearing, collapsing, or rebounding. Heat death remains the leading theory, not because it is the most dramatic, but because it is the one most consistent with what we see. The first reason lies in the observation of expansion. In the early 20th century, Edwin Hubble discovered that galaxies are receding from us. Their light stretched to longer wavelengths as space expands. This was the first hint that the universe is not static, but dynamic, with space itself growing over time. Later, the discovery of the cosmic microwave background provided confirmation. This faint glow, a relic of the Big Bang, showed that the universe began hot and dense and has been cooling ever since. Expansion has been written into the cosmos from the very beginning. At first, scientists assumed that gravity might slow this expansion. After all, galaxies are massive, and gravity is universal. Perhaps expansion would decelerate, eventually halting, maybe even reversing. That idea allowed for possibilities like the Big Crunch. But observations in the late 20th century changed everything. Measurements of distant supernovas showed that expansion is not slowing, it is accelerating. Galaxies are flying apart faster than before, driven by something we now call dark energy. This discovery was decisive. An accelerating universe makes a crunch unlikely. If space is expanding faster and faster, gravity cannot pull everything back together. There is not enough matter to reverse the process. Instead, the universe will keep growing, stretching galaxies away from one another until they are isolated, until even light from distant regions cannot reach us. Expansion, not contraction, sets the stage. The second reason heat death remains the leading theory is entropy. The second law of thermodynamics tells us that entropy always increases in a closed system. The universe, as far as we can tell, is just such a system. Energy is conserved, but its usefulness diminishes as it spreads. Stars burn and fade, remnants cool, black holes evaporate step by step, gradients vanish. The natural endpoint of this process is maximum entropy, a state where everything is uniform, balanced, incapable of further change. That is heat death. Every observation we have supports this trend. Stars are not eternal. We see them exhaust their fuel. Galaxies evolve, using up their gas for star formation until nothing remains. Radiation stretches as space expands, shifting from bright light to faint microwaves, and eventually to radio waves so long they blur into background noise. Black holes, once thought permanent, are shown by theory to radiate away. Each piece of evidence fits into the same puzzle. The universe is heading toward equilibrium. A third reason is the stability of dark energy as we currently understand it. The Big Rip depends on dark energy growing stronger over time. The Bounce and the Crunch depend on dark energy behaving differently, or perhaps not existing at all. But the best data so far suggests that dark energy is constant, a steady property of space itself. If that remains true, acceleration continues at its current pace, enough to separate galaxies, but not enough to tear atoms apart. This is the exact condition that leads to heat death. Of course, science is always provisional. We do not know everything about dark energy. We do not yet have a complete theory of quantum gravity. Surprises are possible. But among the models that fit what we know, heat death is the simplest, the most straightforward, the most consistent with both thermodynamics and observation. That makes it the leading theory. Another reason for its prominence is that it does not require special exceptions. The Big Crunch requires the universe to have more matter than we observe. The Big Rip requires dark energy to evolve in ways we have no evidence for. The Bounce requires speculative physics we cannot yet test. Heat death, by contrast, requires only that current laws keep working as they have. No changes, no reversals, no hidden twists. Just the same processes continuing across longer and longer spans. This does not mean it is less profound. If anything, the quietness of heat death makes it more striking. The universe does not need a dramatic climax. It simply follows its rules to their natural conclusion. The stars shine because fusion turns fuel into energy. The galaxies expand because space itself stretches. Entropy rises because it always does. These same processes, unaltered, carry the universe from brilliance to silence. There is also a psychological reason scientists often prefer the heat death scenario. It emphasizes continuity with the present. We can already see the processes at work. We see stars exhausting themselves. We see galaxies drifting. We see the cosmic background cooling. Heat death is not a leap of imagination into completely different physics. It is an extrapolation of what we already observe. That makes it both convincing and unsettling. It says the universe is not headed somewhere different, but simply further along the same road. And yet, even within this scenario, there is room for mystery. The timescales involved are so vast that they stretch language. Numbers like 10 to the power of 100 years are beyond direct human comprehension. Our mathematics allows us to describe them, but our intuition falters. This means that while heat death is the most likely outcome, it still carries the awe of the unknown. It is a destination we can outline but never fully imagine. One might ask why it matters which ending is most likely. After all, the timescales are so far beyond us that they seem irrelevant. But the study of cosmic endings is less about preparing for them, and more about understanding the laws of nature. To know why heat death is the leading theory is to know why stars shine, why galaxies evolve, why entropy rises. It is to understand the direction of time itself. The ultimate fate is a mirror of the present, showing us the consistency of the universe across all scales. It also matters because endings frame meaning. To know that the universe will not collapse in fire or tear itself apart suddenly, but instead fade into stillness, changes how we see the present. It highlights the temporary nature of brilliance, the fleeting age of stars and galaxies. It suggests that our moment here and now is special, not because it lasts, but because it exists at all. So heat death remains the leading theory because it requires no special changes, because it fits every observation, because it is consistent with the deepest laws of physics we know. It may not be dramatic, but it is steady, inevitable, and profoundly revealing. It tells us that the universe does not end in violence, it ends in balance, and in that balance there is a kind of beauty. The same laws that light the stars also dim them. The same rules that build galaxies also dissolve them. The same principle that gives time its arrow also quiets it. Heat death is not just the most likely ending. It is the completion of the story that began with the Big Bang. When scientists speak about heat death, they are not only describing a picture of the far future, they are also holding up a mirror to the present, because the possibility of a universe ending in silence has deep consequences for how physics itself is understood. Heat death is not just a cosmological forecast. It is a reflection of the laws that govern energy, entropy, and time. Thinking about what it means is as much about the foundations of physics as it is about the fate of the cosmos. The most immediate meaning is the universality of the second law of thermodynamics. This principle, that entropy tends to increase, was first noticed in steam engines and simple laboratory experiments. It explained why heat flows from hot to cold, why energy becomes less useful as it spreads, why perpetual motion machines are impossible. What heat death shows is that this principle is not limited to factories or kitchens. It applies to everything. The same rule that governs melting ice also governs galaxies and black holes. Physics has few laws that stretch so far, from the smallest scales of molecules to the widest expanses of space. Heat death is the second law written across the entire universe. This matters because it clarifies the arrow of time. Time is often treated in equations as symmetrical. The fundamental laws of motion do not care whether you run them forward or backward. A ball thrown into the air can be described in reverse, and the math works perfectly. But our lived experience of time is not symmetrical. We remember the past, not the future. We grow older, not younger. We see eggs crack, not uncrack. Entropy resolves this difference. It explains why time feels like it flows one way. The fact that heat death is the most probable future means that the arrow of time is not just a perception. It is a reflection of the way energy distributes itself. The concept also sharpens questions about the universe's beginning. If entropy always increases, why did the universe begin in a state of such low entropy? The Big Bang was incredibly hot and dense, but in terms of entropy it was remarkably ordered. That starting condition is still one of the biggest mysteries in physics. Why did the cosmos begin in a way that allowed for structure, stars, galaxies, and eventually life? Heat death emphasizes this mystery by showing the contrast. The end state is high entropy, maximum disorder, featureless. The beginning was the opposite. Understanding why may be key to a deeper theory of cosmology. Heat death also intersects with the study of information. In physics, entropy is not only about heat and energy, it is also about knowledge. Higher entropy means less information about the details of a system. A scrambled egg has more entropy than an unbroken egg, because the precise arrangement of molecules is harder to track. In cosmology, this principle raises questions about whether the universe forgets as entropy rises. Heat death implies that in the end all information is blurred, smeared out, inaccessible. The details of every star, every planet, every life lost to uniformity. Yet some physicists argue that information cannot truly be destroyed, that it may be preserved in subtle ways, perhaps encoded in radiation. Black holes and Hawking radiation are central to this debate, and heat death sharpens the stakes. If the universe ends in equilibrium, where does the information go? Another meaning lies in the role of dark energy. Heat death assumes that dark energy is constant, that expansion continues steadily without dramatic changes. If this is true, then the universe's fate is sealed. But dark energy remains mysterious. It is the majority of the cosmos, yet we know almost nothing about it. By pointing to heat death, physicists are also pointing to a challenge: to understand the nature of dark energy in detail. If it evolves over time, if it has hidden properties, then the ending could change. So every new observation of cosmic expansion is not just a check on the present, it is a probe into the future. Heat death also pushes physics toward its limits in another way. It raises the question of whether time itself can exist without change. If entropy reaches a maximum and nothing happens anymore, is time still meaningful? Some theories suggest that time and change are inseparable, that in a timeless universe time itself has no role. Others suggest time continues mathematically, even if there are no events to mark it. Heat death forces this question into the open. Physics does not yet have a definitive answer, and the debate touches the deepest foundations of how we think about reality. In addition, heat death carries implications for the search for a theory of everything. Our current picture of physics is split between general relativity, which describes gravity and the structure of space-time, and quantum mechanics, which governs particles and fields. These two frameworks do not always fit together smoothly. Black holes, in particular, are places where they clash. Heat death, by including the evaporation of black holes, brings these frameworks together. To fully understand the universe's fate, physics must unite its theories. Heat death is not just an ending, it is a test, pointing to gaps in our knowledge and pushing us toward deeper unification. Even beyond physics itself, heat death has philosophical weight. It underscores the impermanence of everything. No structure, however vast, survives forever. Stars, galaxies, even black holes all fade. For physics, this is not a cause for despair, but a confirmation of consistency. The same rules apply everywhere, always. The cosmos does not make exceptions, even for its most impressive creations. This consistency is one of the triumphs of science. The universe plays fair. It obeys its own laws to the end. But heat death also highlights the limits of those laws. When we speak about timescales of 10 to the power of 100 years, we are stepping far beyond what can ever be observed. No experiment, no observation will ever confirm directly what happened so far ahead. Heat death is a conclusion drawn from extending current laws into the future. If those laws hold, the prediction follows. But if new physics emerges, the story could change. In that sense, heat death is not just a theory of the future, it is a measure of our present confidence in the laws we know. This duality, certainty in principle, uncertainty in detail, is part of what makes heat death so profound. It shows how much we can understand and how much we may still be missing. Physics, at its best, is always about both. To know that entropy shapes the cosmos is to know something deeply reliable. To wonder whether time itself can persist without events is to admit the mystery is not over. Finally, heat death matters for physics because it frames the human place in the story. We live in the stelliferous era, the age of stars. Entropy is rising, but gradients remain. Energy still flows. Structures still exist. Physics tells us this age is temporary. That does not make it less remarkable. It makes it more so. We live in the thin middle slice of cosmic history, when the universe is both old enough to form complex structures and young enough to still have them. The past was too simple, the future too empty. We are here during the richness. That context is part of what physics gives us. Not just laws and numbers, but perspective. So what heat death means for physics is many things at once. It confirms the universality of entropy. It clarifies the arrow of time. It sharpens the mystery of the universe's beginning. It raises questions about information, dark energy, and time itself. It pushes us toward unifying theories. It affirms the consistency of natural laws, and it humbles us, reminding us that our place in the story is fleeting but luminous. The universe may end in silence, but physics ensures that the silence itself is meaningful. When you look up at the night sky, it is easy to feel small. The stars are distant, the galaxies even more so, and the timescales of cosmic change are beyond comprehension. The universe existed long before you, and it will exist long after. And yet, when scientists trace the long future of the cosmos toward heat death, something surprising emerges. For all its vastness, the universe has only a narrow window in which beings like us can exist. We live not just anywhere in the timeline, but in a brief, extraordinary moment when the cosmos is vibrant, structured, and alive with energy. That context shapes the human place in a winding down universe. To understand this place, it helps to picture the great sweep of cosmic history. The first era was violent and simple, a blaze of energy and particles after the Big Bang. Stars had not yet formed, galaxies had not yet gathered, matter was just beginning to settle into structures. Life, as we know it, was impossible. Later came the stelliferous era, the age of stars. Hydrogen fused into helium, stars ignited, galaxies filled with light. This is the era we inhabit. Planets orbit suns, chemistry flourishes, and life can arise in the gentle balance of energy flowing from stars. It is a middle age of richness, temporary but remarkable. In the future lies the degenerate era, when stars are gone, when galaxies darken, when remnants dominate. That age is inhospitable to life as we know it. Energy will be too sparse, gradients too weak. The universe will be cold, silent, and empty. Between the simple beginning and the empty ending is this luminous middle. That is where we are. This realization changes how we think about ourselves. Humanity often imagines itself as small, insignificant against the backdrop of the cosmos. And in one sense that is true. Earth is a speck in a vast galaxy, which is itself a speck among billions. Your life is brief compared to the age of the stars, but in another sense you are profoundly rare. You are part of a moment that will not last, a moment when the universe is capable of supporting complexity. That rarity makes your place meaningful. Consider the conditions that make your existence possible. A star like the sun shines steadily, not too hot, not too cold, for billions of years. A planet formed at just the right distance, with water and chemistry suited to life. The elements in your body, carbon, oxygen, nitrogen, iron, were forged in stars that lived and died before the sun was born. You are literally made of cosmic history, built from the debris of generations of stars. That chain of events is fragile. It required a universe with the right balance of expansion and gravity, the right mix of elements, the right stability for stars to form and shine. Now place that chain against the backdrop of heat death. Stars will not always shine. Planets will not always orbit. The conditions that allow life are temporary. In trillions of years they will vanish. That means that right now, in this age, the cosmos is as alive as it will ever be, and you are here to witness it. This perspective is not meant to inflate human importance, but to highlight human context. You're not outside the universe observing it. You are part of it, a product of its temporary richness. Your thoughts, your experiences, your very sense of wonder about the universe are part of the story Entropy is telling. The winding down cosmos includes not just galaxies fading, but also beings reflecting on their place within it. Psychologically, this duality can be both humbling and empowering. Humbling, because it reminds you how fleeting your existence is, how temporary your world is, how small your place is in time and space. Empowering, because it shows that your existence, fleeting as it is, belongs to a rare window of possibility. You are alive at a moment when the universe allows for life, thought, and meaning. That is extraordinary. It also suggests a way of thinking about purpose. If the cosmos is winding down, and nothing lasts forever, then meaning cannot come from eternity. It must come from the present, from what exists now. Stars are meaningful because they shine while they can. Life is meaningful because it flourishes in the conditions that permit it. Human actions, human creations, human loves and struggles gain value not from their permanence, but from their participation in this fleeting age. The winding down of the cosmos does not erase purpose, it frames it. There is also comfort in the thought that humans, though brief, are not disconnected from the larger story. The atoms in your body will one day return to the cosmos, scattered into whatever comes next. You are temporary as a person, but as matter and energy, you are continuous with the universe itself. The winding down cosmos will one day include your atoms, your particles, still present even when stars and galaxies are gone. In that sense, you are part of the universe's memory. And beyond atoms, there is something else. The fact that you can reflect on heat death at all is itself part of the cosmic story. The universe has become aware of itself, briefly, through beings like you. That awareness may not change the ultimate outcome, but it changes the journey. It adds a layer of meaning the cosmos would not otherwise have. For a brief time, the universe is not only matter and energy, it is also thought and wonder. That too is part of the winding down. Imagine someone in the distant future, perhaps billions of years from now, living under the dim light of the last red dwarfs. Their night sky will be different. The galaxies will have drifted beyond view. The stars will be fewer. But even they, if they exist, will be living in this luminous middle, still part of the rare age of richness. And perhaps they too will look back, imagine the long future, and feel the same mix of humility and awe. The human place in a winding down cosmos is not at the beginning, and not at the end, but in the middle. It is the place of witnesses, of participants in the universe's active era. To recognize that is not to diminish humanity, but to honour the rarity of being here at all. Out of all the possible times the universe could exist, you are alive in the age when stars still shine, when galaxies still glow, when meaning can still be made. So when you think of heat death, do not think only of silence and ashes. Think also of the present, of the extraordinary chance to exist in this vibrant window. The cosmos will wind down, but right now, it is alive, and so are you. Thank you for staying with this story as it wound its way through time, stars, galaxies, and endings. We began with campfires in the sky, with suns burning brightly in the darkness, and we followed their paths into fading embers, into black dwarfs, into black holes. We walked alongside gravity as it held things together and alongside entropy as it spread them apart. We imagined the faint glow of Hawking radiation, the silence that comes when even the strongest structures disappear, and the long, patient stillness of heat death itself. Now, at the end of this journey, it feels right to let the universe's story settle into quiet, like a lullaby carrying you toward rest. The image of heat death is simple and profound. It is not fire or destruction. It is not chaos or violence. It is quiet. It is the spreading of energy into evenness, the smoothing out of every difference, the soft fading of every flame. In this future, there is no tragedy and no triumph, only balance. The cosmos that once burned so brilliantly does not rage against its ending. It simply exhales. There is comfort in this. Because if the universe itself rests, then rest is not something small or shameful. It is part of the rhythm of everything. Stars rest when their fuel is gone. Black holes rest when their energy is spent. Galaxies rest when their stars fade. And eventually the universe rests too. Rest is not failure, it is completion. It is the final note of the song, still resonant even after the sound has gone. As you listen to this, you are part of that rhythm. Your life is a tiny echo of the same pattern. You rise, you shine, you burn with energy, and then you rest. The universe does not resist this, and neither do you have to. In the stillness of the cosmos, there is an invitation to stillness within yourself. Close your eyes for a moment and imagine the night sky above you. Not the sky of the far future, not the empty silence of heat death, but the sky you know now. The Milky Way arching across in soft light. Stars scattered like sparks on black velvet. Planets shining steadily. That sky is temporary, yes, but temporary does not mean meaningless. It means precious. To see it, to exist in this moment when the universe is bright, is a rare gift. Out of all the possible times in cosmic history, you are here, alive, with stars still glowing above you. And now picture the sky of the far future. A darker sky with only red dwarfs glowing faintly. Then darker still as the dwarfs fade into silence. Then darker yet as black holes whisper their last radiation. Until at last, there is no light left at all. Only the thin evenness of equilibrium. This image is not frightening when you let it unfold slowly. It is gentle, peaceful, inevitable. It is the cosmos completing its journey. In that silence, there is no loneliness, because everything that ever was is still there, dissolved into the background, blended into the ashes, carried in the faintest traces of radiation. The memory of stars, the memory of galaxies, the memory of lives, all of it is still present, transformed but not erased. The universe does not forget. It only softens its details, letting them blur into stillness. So as you drift towards sleep, think of this cosmic lullaby. The rise and fall of stars, the dance of galaxies, the patient work of gravity, the steady increase of entropy. All of it has been one long song, and you're hearing it now in one of its brightest verses. The notes ahead are quieter, fading slowly, but they are still part of the same melody, a melody of beginnings, middles, and endings. There is a tenderness in knowing that endings are natural. They do not take away what has come before, they complete it. The universe's stillness does not erase its brilliance, it honours it. Every burst of light, every orbit, every atom, every thought is written into the story. The ending is not a negation, but a resting place, and so, as the universe will rest one day, so can you rest tonight. You do not need to resist it. You do not need to hurry. The cosmos has taken billions of years to unfold, and it will take trillions more to fade. Your night can be calm, your body can be still, your mind can soften, like galaxies drifting into distance, like stars dimming gently, like black holes whispering their last light. Breathe slowly, in and out. Feel the rise and fall, like the rise and fall of cosmic ages. Each breath is its own cycle, a beginning, a middle, an end. With each exhale, you settle deeper into quiet. With each inhale, you remind yourself you are part of this universe sharing its rhythms. Nothing separate, nothing outside, just one more expression of the same laws, and as you listen, let the weight of time lift off your shoulders. You do not need to hold the future. You do not need to carry the thought of heat death with you. It is enough to know that the universe is steady, that its laws are patient, that everything has its place. The future is vast, but your present is here, and it is gentle. So let this story lull you, the story of a universe that began in brilliance and will end in stillness, a story that carries stars and galaxies, life and thought, all the way to silence. And as you drift into sleep, let that silence become your silence. Let the universe's rest become your rest. The cosmos sings a lullaby, not in words, not in sound, but in the rhythm of its rise and fall. Tonight, you're listening to that lullaby, and it will carry you gently into dreams. Thank you for listening, and for letting this story of the universe accompany you tonight. If you found this journey soothing, you can stay with this space whenever you need calm, curiosity, and rest. Each time you return, there will be another story waiting, another quiet exploration of science and wonder. For now, let the stars, the galaxies, and the silence of the cosmos fade into the background of your mind. Rest deeply, dream gently, and carry the calm with you into tomorrow. Good night.